Every time you look up at the night sky, you're gazing into a vast cosmic library, a silent, glittering record of everything that has ever happened in our universe. But what if I told you that each of those stars is not just a point of light, but a living memory, a storyteller holding secrets billions of years old? Imagine if stars could speak. What ancient whispers would they share about the violent, beautiful chaos that formed them, about the galaxies that gave them life? Today, we begin an extraordinary journey to uncover exactly that. What stars remember. We're going to explore how these distant suns carry within them the very history of the cosmos, imprinted in their light, their motion, and even the elements that compose them, the same elements that make up you and me. This isn't just astronomy, it's cosmic archaeology. We're going to learn how to read the memories of stars, to decode the tales of galactic collisions, the echoes of the Big Bang, and the quiet, persistent evolution of galaxies over incomprehensible spans of time. These stellar memories connect us directly to the birth of the universe itself. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the hearts of ancient stars and scattered across space by titanic supernova explosions. You are, in the most literal sense, made of stardust, and that stardust remembers where it came from. By the end of our journey together, you won't just see the night sky as a beautiful spectacle. You'll understand it as a dynamic, living archive, a grand, evolving story written in light and element, motion and time. We'll uncover how galaxies grow, change, and even cannibalize one another, leaving behind clues in the stars they leave in their wake. From the faint, ancient suns wandering the halo of our Milky Way to the brilliant young stars lighting up spiral arms, each has a role in this cosmic narrative. So join me as we learn to listen to what the stars remember, and in doing so, discover not just the history of our galaxy, but our own place within this astonishing universe. Think of a star not as a simple beacon of light, but as a meticulous archivist. From the very moment it ignites fusion in its core, it begins its work, diligently preserving a perfect record of the cosmic neighborhood it was born into. The key to this incredible record-keeping lies in the composition of the gas cloud that collapsed to form it. As a star forms, it essentially samples the chemical makeup of that cloud, locking those elemental ratios into its outer layers, its atmosphere. This isn't just a snapshot, it's a fossilized sample of that specific place and time in the galaxy's history, preserved for billions of years. This is why astronomers get so excited about stellar spectroscopy. By breaking a star's light into a rainbow spectrum, they can read these faint chemical fingerprints. They can see the specific signatures of hydrogen, helium, and crucially, all the heavier elements that astronomers collectively call metals. The amount of these metals, a property known as metallicity, is the star's most fundamental memory. It tells us immediately about the environment that came before it. A star born from a cloud that had been polluted by many generations of previous stars will be metal-rich, shining with the recycled remnants of long-dead giants. But a star formed from pristine, unpolluted gas will be metal-poor, a relic from a much earlier, more primitive time. This is why the oldest stars we find, often lurking in the sparse halo of our galaxy or within ancient globular clusters, have such incredibly low metallicities. They remember a universe before planets, before complexity, when the cosmos was a much simpler place composed almost entirely of hydrogen and helium. In contrast, a younger star like our Sun, born in the crowded galactic disk, has a much richer chemical story to tell. Its higher metal content is a direct inheritance from countless supernovae that exploded over eons, seeding its birth cloud with the elements that would eventually form our solar system and everything in it. By cataloging the chemical compositions of stars across the Milky Way, we can do more than just date them. We can map the galaxy's chemical evolution over time. It's like being an archaeologist who can date a piece of pottery not just by its style, but by performing a chemical analysis of the clay itself to determine exactly which quarry it came from and when it was fired. These stellar time capsules allow us to reconstruct chapters of galactic history that we could never directly observe, reading the story of our galaxy's growth and transformation written in the elements of its stars. So if stars are the historians of our galaxy, then the very oldest among them are the archivists of a lost age. They hold the first and most fundamental memory of all, an echo of creation itself. To understand this, we have to journey back to a time before metals, before planets, before even the first galaxies fully took shape. We have to picture the universe in its raw infancy, just minutes after the Big Bang. In that unimaginable heat and density, the first atomic nuclei were forged in a process called Big Bang nucleosynthesis. For about 17 minutes, the entire cosmos was a nuclear fusion reactor, producing the two simplest elements, hydrogen and helium. And then it stopped. The universe expanded and cooled too rapidly for anything heavier to form. This left the cosmic canvas almost entirely blank, a vast, pristine soup of about 75% hydrogen and 25% helium by mass, with only the tiniest trace amounts of lithium. For hundreds of millions of years, this was everything. This is the pure, primordial composition that the first stars were born from. Theoretical astrophysicists call these first-born suns population 3 stars. We haven't found one yet. They are the holy grail of modern astronomy, but their existence is a cornerstone of our models of cosmic evolution. Imagine a star unlike any we see today. A star with 0 metals, a star whose composition was a perfect, untouched reflection of that initial Big Bang recipe, because they formed from gas that had never been enriched by previous stellar generations. These stars were likely behemoths, hundreds of times more massive than our Sun. Their immense mass meant they lived fast and died young, burning through their nuclear fuel in just a few million years before exploding as incredibly powerful supernovae. In their violent deaths, they achieved what the Big Bang could not. They forged the first heavy elements, the first metals like carbon, oxygen, and iron, and they blasted them out into the void, polluting the cosmos for the very first time and setting the stage for everything that would follow. While the search for a true population 3 star continues, we have found their next of kin, and these ancient survivors are what allow us to hear this faint primordial echo. These are the extremely metal-poor stars, and they are the closest thing we have to a time machine. A star like He 1327, 2326 is a perfect example. Its atmosphere contains iron at a level over 1 million times lower than our Sun's. To put that in perspective, if the Sun's iron content were a full-sized swimming pool, the iron in this star would be barely a single drop. This isn't just a little bit metal poor. This is a relic that formed from gas that had only been lightly sprinkled with the ashes of perhaps 1 or 2 of those first population 3 supernovae. By studying the precise ratios of elements in stars like this, astronomers can perform a kind of cosmic forensics. They can work backwards to figure out what kind of star first polluted their birth cloud, effectively fingerprinting the very first supernova and understanding their explosive yield. This primordial memory isn't just about chemistry, it's also a vital clue to the role of dark matter. the first structures in the universe, the tiny fluctuations that would eventually grow into galaxies, were dominated by dark matter. It was the gravitational scaffolding upon which normal matter, that hydrogen and helium gas, could collect and eventually collapse to form the first stars. The properties of the oldest stars we can find, their locations and their motions, tell us about the nature of that scaffolding. Did the first stars form in isolation or in small clusters? Their distribution helps us test our theories about how dark matter behaves and how it shaped the cosmos from the very beginning. So every time we analyze the light from one of these ancient metal-poor stars, we're not just measuring elements. We are listening to a faint whisper from the dawn of time, a direct probe into the conditions of the universe when it was less than 1 billion years old, confirming our deepest theories about its origin and setting the immutable starting point for the entire cosmic story of enrichment that we are about to explore. So if the primordial composition is the first faint whisper from the Big Bang, then metallicity is the booming, unmistakable voice of a galaxy hard at work, a detailed chemical fingerprint that tells a rich story of life, death, and cosmic recycling. Think of it this way: every star is born with a specific chemical passport stamped by the galactic neighborhood of its birth. This passport's most important visa is its metallicity, which astronomers define as the fraction of a star's mass that is made up of any element heavier than helium. Now, that might sound like a technicality, but it's everything. It's the single most telling clue about the history of the gas cloud that collapsed to form that star. A high metallicity star, like our Sun, is a child of privilege, born into a region that has already seen countless generations of massive stars live and die. Each of those stellar deaths was a contribution, a legacy of newly forged elements blasted into space, enriching the raw material for the next round of star formation. This is why stars in the bustling galactic disk, where star formation has been continuous and prolific, tend to be metal-rich. Their high iron content is a direct inheritance, the accumulated wealth of eons of stellar labor. On the flip side, a star with extremely low metallicity is an ancient aristocrat, a relic from a time before this great enrichment got into full swing. These metal-poor stars are the galactic hermits, often found in the quiet, sparse halo that surrounds the main body of a galaxy like our Milky Way, or in the isolated, undeveloped dwarf galaxies that orbit it. They formed from gas that had been touched by very few, if any, previous supernova. The current record holder for this cosmic purity is a star with a name only an astronomer could love, SMSSJ 031300, 36,670,839, 3. Analysis of its light reveals an almost unimaginable scarcity of iron. Its iron content is so low that astronomers couldn't even measure a ratio, they could only determine an upper limit. It's not just 1 million times lower than the Sun, it's at least 10 million times lower. This isn't just a little bit metal poor, this is a fossil from a time when the very concept of a planet was an impossibility. The most fascinating part is its peculiar chemical signature. While it has almost no iron, it does have detectable amounts of carbon. This bizarre combination is like a cosmic crime scene clue. It suggests this star didn't form from gas polluted by a typical, high-energy supernova. Instead, the best explanation is that its birth cloud was seeded by the ashes of just one single, very first-generation star, a population Roman III star that was likely over 200 times the mass of our Sun. This behemoth would have had a peculiar death. Its core might have collapsed directly into a black hole, trapping the newly forged iron inside and preventing it from being scattered into space, while a weaker shockwave ejected its outer layers, rich in lighter elements like carbon, into the surrounding void. This one event provided just enough enrichment to allow a second generation of stars, including SMSS J031300 to form. This single star's metallicity, or lack thereof, tells a shockingly specific story about a single cataclysmic event that occurred over 13 billion years ago. This pattern repeats itself on a grand scale, creating what's known as a metallicity gradient across entire galaxies. In a spiral galaxy like our own, if you were to take a grand tour from the crowded inner bulge out to the lonely outer reaches of the disk, you would measure a steady and clear decline in the average metallicity of the stars. This isn't random, it's a direct map of the galaxy's chemical evolution. The inner regions, dense and crowded, experienced rapid, intense waves of star formation early on. This led to a faster buildup of metals, meaning stars forming there more recently were born into an already rich environment. The outer regions, however, are the galactic suburbs where star formation has always been a slower, more sporadic process. The gas there has been less polluted by successive generations of supernova, so the stars that do form are more chemically primitive. By meticulously charting these gradients, astronomers can read a galaxy's growth chart. They can see how star formation began in the core and gradually spread outward, painting the galaxy in ever heavier elements over billions of years. The metallicity of a star is more than just a number. It's a timestamp, a location tag, and a detailed report on the industrial activity of its birthplace, all encoded in the very fabric of its light. But the story of galactic enrichment isn't just a simple tally of elements. It's a detailed chemical detective story written in the specific patterns of those elements, a record of exactly how they were created and delivered. This brings us to one of the most powerful memories a star can hold, the unmistakable signature of the supernova that came before it. A star's composition isn't just a list of ingredients, it's a detailed recipe book that tells us which cosmic chefs were working in the kitchen and when they clocked in. The key to reading this book lies in understanding that not all stellar explosions are created equal. They leave behind very different chemical fingerprints. Massive stars, those born with more than about 8 times the mass of our Sun, live fast and die young. Their furious burning fuses elements up to iron in their cores in just millions of years. When their cores finally collapse, they trigger titanic core collapse supernova. These explosions are the universe's primary foundries for a specific group of elements known as the alpha elements. These include oxygen, neon, magnesium, silicon, and calcium. The process that creates them, alpha particle capture, is incredibly efficient in the final, frantic moments of a massive star's life. So when one of these giants explodes, it floods its surroundings with these specific building blocks. A star that forms from a cloud polluted by these events will be born with a distinct chemical advantage in these alpha elements. Then there's the other great class of cosmic explosions, type Ia supernova. These aren't the deaths of single, massive stars, but rather the spectacular thermonuclear detonations of white dwarfs, the ancient, dense cores of lower mass stars. If a white dwarf in a binary system steals enough material from its companion to push it over a critical mass limit, it undergoes a runaway fusion reaction that completely obliterates it. The physics of this detonation is perfect for forging a different set of elements, the iron peak elements. This group includes iron itself, but also nickel, cobalt, and manganese. A type Ia supernova is essentially a cosmic bomb that manufactures and flings out immense quantities of iron group elements into the galaxy. The true power of this stellar memory comes from comparing the abundances of these two groups. Astronomers do this by looking at ratios, most famously the ratio of oxygen to iron, written as O/Phi. Think of this ratio as a cosmic clock. In the very early universe, the first stars to die were the massive, short-lived ones. They went off as core collapse supernova, seeding the pristine gas with alpha elements like oxygen. At this point, there was very little iron around. So, the very next generation of stars to form from this newly enriched gas inherited a high O/Phi ratio. Their chemical passport was stamped almost exclusively by massive stars. Type Ia supernova take much longer to occur. A white dwarf is the end stage of a star that lived a long, quiet life, and then it has to slowly accrete mass from a companion. This process can take billions of years, so after a long delay, these events began to contribute their enormous iron yield to the galactic mix. This influx of iron from Type Ia supernova effectively dilutes the O/Phi ratio over time. Therefore, when we find an ancient star with a high O/Phi ratio, we are looking at a fossil that formed during the galaxy's wild youth, a time dominated by the rapid, violent deaths of massive stars. A younger star, like our Sun, has a lower O/Phi ratio because it was born after the slower, iron-producing Type Ia supernova had a chance to contribute their wealth to the galactic treasury. By measuring this ratio in thousands of stars, astronomers can construct a detailed timeline of star formation and death throughout a galaxy's history, distinguishing between eras of rapid, massive star formation and the later, more measured pace of galactic chemical evolution. This precise elemental accounting reveals that the universe doesn't just make elements, it makes them on a schedule, and the stars remember that schedule with impeccable accuracy. But the cosmic foundry has more than one way to forge the elements, and some of the most valuable and fascinating ones require the most extreme and violent of all cosmic events. For decades, astronomers wrestled with a great mystery. Where in the universe do the very heaviest elements like gold, platinum, and uranium actually come from? We knew they couldn't be made in the regular furnace of a living star or even in a standard supernova. Creating these atomic behemoths requires a flood of free neutrons so dense and rapid that atomic nuclei can be bombarded and built up to immense sizes almost instantly. This is called the rapid neutron capture process, or R process for short. The question was, what natural event could possibly provide such an insane environment? The answer turned out to be one of the most energetic and rare spectacles in the cosmos, the collision of two neutron stars. Imagine the remains of two dead stars, each so dense that a single sugar cube-sized piece of one would weigh as much as a mountain here on Earth. These ultra-dense cores, each only about the size of a city, are locked in a final, fatal dance, spiraling inward over millennia until they finally slam together. The collision is almost beyond comprehension. It releases more energy in a fraction of a second than our Sun will emit in its entire 10 billion-year lifetime. In the furious aftermath of this merger, a small fraction of the neutron star material is blasted out into space, and it is in this expanding cloud of ultra-hot, neutron-rich debris that the magic happens. The conditions are perfect for the R process. Atomic nuclei are bombarded by a tsunami of neutrons, growing heavier and heavier in a blink of an eye, creating a full periodic table's worth of the heaviest elements all at once. This material, now rich in gold, platinum, and other rare earth elements, eventually cools and mixes with surrounding clouds of gas and dust. Then, millions of years later, when that enriched cloud collapses to form a new generation of stars, those elements are woven into the very fabric of the newborn suns. This isn't just theoretical anymore. We have direct evidence written in starlight. Take a star with the less than poetic name HD 222,925, located in the halo of our Milky Way. When astronomers analyzed its spectrum, they found something astonishing. This star is absolutely littered with R process elements. Its atmosphere contains detectable amounts of gold, platinum, uranium, and a host of other rare heavy elements, 42 in total. This is the cosmic equivalent of finding a single coin minted from the treasure of a specific, legendary pirate ship. The incredibly high abundance of these elements in this one star is a dead giveaway. It tells us with near certainty that the cloud of gas from which HD 222,925 formed was seeded by the debris from a single, nearby neutron star merger event that occurred just before its birth. It's a direct chemical snapshot of that cataclysm. By finding and studying more stars like this, astronomers are beginning to do something incredible. They are mapping the history of these most violent of cosmic explosions throughout our galaxy. They can start to answer questions like, how often do these mergers happen in a galaxy like ours? Do they tend to occur in specific regions like the crowded galactic center or out in the quieter suburbs? Each R-process-enhanced star is a data point, a marker on a galactic map that says, a spectacular event happened here once. This stellar memory doesn't just satisfy our curiosity about exotic astrophysics. It literally explains the origin of the precious metals that shape our human world. The gold in a wedding ring, the platinum in a catalytic converter, the uranium that can power a city, all of it was forged in the heart of a neutron star collision that occurred billions of years ago, far across the galaxy. The fact that these elements eventually found their way into a cloud that formed our solar system and then into the planet we call home is a breathtaking connection between the most violent events in the universe and our everyday existence. So far, we've been reading the stories written in a star's chemical composition, but that's only half the tale. To get the full picture, we need to see these stars in motion to understand the paths they travel through the galaxy. It turns out that a star's orbit is a profound and dynamic memory, a permanent record of its origin story written not in elements but in velocity and trajectory. Think of it like this: you can tell a lot about a person's history by whether they've lived in the same small town their entire life or if they've traveled the world, picking up languages and customs along the way. Stars are the same. A star's path through the galaxy is its travelogue, and it never forgets where it came from. Stars that form naturally from the calm, rotating disk of a galaxy like our Milky Way inherit a very orderly, predictable motion. They settle into nearly circular orbits, rotating placidly around the galactic center in the same direction as the vast majority of their neighbors, much like cars all driving the same way on a gigantic cosmic freeway. These are the homebodies of the galaxy, the stars born in situ, and their smooth, cooperative orbits speak of a quiet, undisturbed upbringing within the main galactic disk. But then there are the travelers, the immigrants. Their stories are written in wild, chaotic paths that immediately stand out. These stars often have highly elongated, eccentric orbits that plunge them from the distant galactic halo right in towards the bustling center and back out again on a dramatic roller coaster ride. Even more telling are the rebel stars on retrograde orbits, moving in the exact opposite direction to the galaxy's dominant spin. This is the cosmic equivalent of driving the wrong way down that galactic freeway at breakneck speed. It's not something that happens by accident within a settled system. A retrograde orbit is a glaring signpost that screams, "I am not from here." These stars are the survivors of galactic cannibalism, the captured remnants of smaller dwarf galaxies that ventured too close to the Milky Way's immense gravitational pull and were torn apart, their stars scattered like cosmic confetti and adopted into a new home. The most spectacular example of this is the discovery of Gaia Enceladus, sometimes called the Gaia sausage. This isn't a new galaxy we can see today. It's a ghost, a phantom structure detected solely by the shared, peculiar motions of millions of stars now residing in our galaxy's halo. Data from the European Space Agency's Gaia mission, which is meticulously mapping the positions and motions of over 1 billion stars, revealed that a huge population of these halo stars were all moving in similar, highly eccentric and often tilted orbits. This cohesive yet chaotic motion was the undeniable fingerprint of a single, massive dwarf galaxy that collided with and was devoured by the nascent Milky Way around 8 to 10 billion years ago. This catastrophic merger didn't just add stars, it fundamentally shaped our galaxy, likely contributing to the formation of the thick disk and dramatically altering the course of the Milky Way's early evolution. Every star that was once part of Gaia Enceladus still carries the kinematic memory of that colossal encounter billions of years after the event itself concluded. By compiling these individual stellar travelogues into a grand map, missions like Gaia are allowing us to perform nothing short of galactic paleontology. We are digging through the kinetic layers of the Milky Way to unearth its assembly history. We can now identify not just Gaia Enceladus, but other, smaller streams of stars, the lingering tidal tails of globular clusters or other dwarf galaxies that are still in the process of being digested. This kinematic archaeology provides a timeline, allowing us to say which merger happened when and how each event contributed to the galaxy we see today. It's a dynamic record that proves the long-held theory of hierarchical galaxy formation, the idea that large galaxies are not born in their current majestic forms, but are built over cosmic time through a relentless process of attracting, absorbing, and assimilating smaller neighbors. The serene beauty of the night sky belies a violent history of construction, and every star's motion is a silent witness to that epic story of growth and change. While individual stars act as solitary historians, sometimes the most detailed chapters of galactic history are written not by lone voices, but by entire communities speaking in unison. These are the star clusters, both the ancient, densely packed globular clusters and the younger, looser open clusters. They are not random collections of stars, they are true stellar families, all born from the same immense cloud of gas and dust at nearly the same moment in cosmic time. This shared origin makes them something far more powerful than a simple group. They are pristine, fossilized snapshots of a specific galactic environment, frozen in time and preserved for billions of years. Because every star in a cluster originates from the same raw material, they all begin life with an identical chemical passport. They share the same age, the same initial composition, and the same initial motion through space. This incredible uniformity turns an entire cluster into a single, massive data point for astronomers, a controlled laboratory for studying stellar evolution and the conditions of the ancient galaxy. Consider the ancient globular cluster M92, a glittering sphere of hundreds of thousands of stars orbiting in the halo of our Milky Way. When we analyze its light, we are looking back in time over 12 billion years. The stars in M92 are among the oldest objects we have ever identified, and their collective chemical signature is a direct window into the Milky Way's infancy. They are extremely metal-poor, confirming they formed from gas that had been enriched by only the very first few generations of stars. Their tightly bound spherical shape and ancient age tell us they were among the first structures to coalesce, even before the Milky Way's majestic spiral disk had fully taken shape. Studying a cluster like M92 is like finding a perfectly preserved archaeological site from a long-vanished civilization. Everything within it tells a consistent story about the era it came from. But the story these clusters tell isn't always one of quiet, in-place formation. Some of them are glaring anomalies, cosmic immigrants that point to a violent history of galactic mergers and acquisitions. The most famous example is the magnificent Omega Centauri. To the naked eye, it looks like a fuzzy star, but through a telescope, it reveals itself as the largest and brightest globular cluster in our sky. However, for a long time, astronomers suspected it was an imposter. It's far more massive, more flattened, and contains a much wider range of stellar ages and metallicities than a typical globular cluster. The evidence now strongly suggests that Omega Centauri is not a true globular cluster at all. Instead, it is the stubborn, surviving core of a small dwarf galaxy that was captured by the Milky Way's gravity long ago. The outer layers of that dwarf galaxy were stripped away and scattered into the halo, but its dense heart survived the encounter intact. It's a galactic ghost, a trophy from a past conquest, its very presence confirming that our galaxy grew by consuming its smaller neighbors. By cataloging and studying the vast family of clusters within a galaxy, astronomers can assemble a detailed scrapbook of its entire life. The ancient globular clusters in the halo record the chaotic, early days of formation. The younger open clusters scattered throughout the galactic disk document periods of more recent star formation, each one a timestamp of when a particular molecular cloud collapsed. And the oddities, the clusters with strange kinematics or chemical spreads like Omega Centauri, serve as permanent markers of past collisions and mergers. Together, they allow us to piece together a timeline not just of star formation, but of the galaxy's entire assembly history, showing how it built itself up from a humble cloud of primordial gas into the grand, structured island of stars we call home today. These stellar families, bound together by gravity and a shared origin, provide the context that turns individual stellar memories into a coherent galactic-scale narrative. But the story of galactic memory isn't always a solo performance. Sometimes it's a duet, a complex dance between two stellar partners whose intimate interactions can rewrite their individual histories and reveal secrets about their shared past. We now turn to the fascinating world of binary star systems, where two stars are locked in a mutual orbit, often for billions of years. This gravitational partnership creates a unique and powerful recorder of cosmic events because the lives of these stars become deeply intertwined. Material can flow between them, their orbits can be perturbed by external forces, and one star's dramatic evolution can directly and permanently alter the composition of its companion. This makes binary systems not just double points of light, but dynamic laboratories where we can observe processes that are impossible to see in a single, isolated star. Perhaps the most direct way a binary system preserves a memory is through the literal transfer of matter from one star to the other. This process, called mass transfer, can leave an indelible chemical mark on the receiving star, a kind of cosmic tattoo that tells a story of stellar evolution and death. A perfect example of this are the so-called barium stars. These are typically older, red giant stars that show a puzzling and significant overabundance of elements like barium, strontium, and other rare earth metals. For a long time, this was a mystery. These elements are created by the slow neutron capture process, or S process, which occurs deep in the interiors of aging, asymptotic giant branch stars. But a single, isolated red giant wouldn't be able to bring these newly forged elements to its surface in such vast quantities. The solution to the mystery requires a partner. Astronomers now understand that a barium star was not always alone. It once had a companion, a slightly more massive star that raced through its life cycle faster. That companion lived, died, and left behind a tiny, dense white dwarf remnant. In its final, dramatic throes as an AGB star, it became bloated and began to shed its outer layers. The barium star, its binary companion, was right there to gravitationally capture a significant portion of this enriched wind. This stellar wind was heavily laced with the S-process elements freshly minted in the companion's interior. The receiving star's atmosphere was thus polluted, its chemical passport stamped not just by the cloud it was born from, but by the death throes of its closest neighbor. Today, we can often still detect the faint white dwarf companion, silently orbiting the enriched giant, serving as the silent witness to this ancient act of cosmic recycling that occurred billions of years ago. Beyond these dramatic chemical exchanges, binary stars serve another critical function for galactic archaeologists. They are nature's premier calibration tools. Determining the precise distance, mass, and age of a single star is incredibly difficult and filled with uncertainty. But a binary system, especially an eclipsing binary where the stars periodically pass in front of each other from our viewpoint, is a gift. By carefully measuring the orbital period, the Doppler shifts in their light as they orbit, and the precise dips in brightness during eclipses, astronomers can directly calculate the star's masses, sizes, and orbital parameters with a level of precision that is otherwise unattainable. These well-characterized binary systems become the fundamental rungs on the cosmic distance ladder. They allow us to calibrate the relationship between a star's true brightness and its other observable properties. This, in turn, lets us accurately measure distances to faraway star clusters and even other galaxies. By knowing the precise ages and compositions of these calibrator binaries in different parts of our galaxy, we can build a much more reliable timeline of galactic evolution, putting firm dates on when different components of the Milky Way formed. Furthermore, the sheer prevalence of binary systems tells us something profound about the conditions of their birth. It's estimated that a majority of Sun-like stars are born with at least one companion. The frequency of these partnerships and the characteristics of their orbits, whether they are wide and separated or tight and close, are a direct reflection of the physical conditions within their natal molecular cloud. Factors like the cloud's turbulence, temperature, and magnetic field strength all influence how a collapsing cloud fragments, determining if it will form a single star or a multiple star system. By surveying the binary populations in star clusters of different ages and densities, we can effectively take a census of star formation environments throughout galactic history. A young, dense cluster like the trapezium in the Orion Nebula is teeming with binaries, showing us the chaotic, crowded conditions of present-day star formation. The older, more dispersed binary systems in the galactic halo, with their wider separations, speak to a quieter, more isolated birth environment billions of years in the past. The binary fraction and their orbital characteristics are themselves a fossil record of the dynamical processes that govern the earliest moments of a star's life, preserving a memory of the crowded stellar nursery they once called home. Just as binary systems tell the story of stellar companionship, another remarkable class of stars holds a different kind of memory altogether, not of their interactions, but of their own internal, rhythmic heartbeat. These are the variable stars, and they serve as the universe's most reliable and precise clocks, their steady pulsations encoding a direct link between their observable rhythm and their true, intrinsic brightness. This incredible property makes them indispensable cosmic yardsticks, allowing us to measure the vast, empty spaces between galaxies and map the large-scale structure of the universe itself. The key to their power lies in a beautifully simple relationship discovered over a century ago, the period luminosity relation. Essentially, the rate at which a certain type of variable star pulses, the length of its cycle from bright to dim and back again, is directly tied to how much total light it actually emits. A star that pulses slowly with a long period is inherently very bright, a true stellar giant. A star that pulses rapidly with a short period is inherently fainter. Once an astronomer times the pulse, they immediately know the star's true wattage. Then, by simply measuring how faint that known wattage appears from Earth, they can calculate the exact distance with astounding accuracy. It's the cosmic equivalent of knowing the precise wattage of a light bulb. If you see it shining dimly in the distance, you can calculate exactly how far away it must be. The historical impact of this discovery cannot be overstated. In the 1920s, the brilliant astronomer Edwin Hubble was peering at faint, fuzzy spiral nebulae through the powerful new Hooker telescope at Mount Wilson. Within these nebulae, like the Great Andromeda Spiral, he identified individual variable stars of the Cepheid type. By meticulously measuring their pulsation periods, he used the period luminosity relation to calculate their distances. The results were earth-shattering. His calculations placed these spirals far, far beyond the confines of our own Milky Way. They were not simple gas clouds within our galaxy, but were themselves island universes, entire galaxies millions of light-years away. This single revelation instantly expanded the known universe by a factor of 100,000, transforming our understanding of our place in the cosmos. But Hubble didn't stop there. By combining these Cepheid distance measurements with other data on how fast these galaxies were moving, he made his second monumental discovery. The farther away a galaxy is, the faster it appears to be receding from us. This was the first direct observational evidence for the expansion of the universe, the foundational piece of evidence for the Big Bang theory. All of this cosmic insight was unlocked by the steady, predictable heartbeat of a special class of pulsating star. Beyond their role as cosmic lighthouses for measuring immense distances, these variable stars are also historians of their own birthplaces, their very existence and properties telling us about the environment that created them. The different types of variable stars act as markers for different eras and locations in a galaxy's history. Take the ancient Lyrae stars. These are old, metal-poor stars that pulse with very short periods, typically less than a day. They are almost exclusively found in the halo of our galaxy and in ancient globular clusters. Their presence in a region is a clear signpost, marking it as a relic from the Milky Way's deepest past, a zone that formed early on and has seen little star formation since. When we map the distribution of Lyrae stars, we are effectively tracing the ghostly outline of our galaxy's primordial structure. In stark contrast, the classical Cepheid variables are the stars of the new generation. They are massive, young, and metal-rich, and they pulsate over periods of weeks. They are found predominantly in the galactic disk, often in or near the vibrant spiral arms where star formation is still an ongoing process. When astronomers find a Cepheid, they are looking at a recent product of the galaxy's active star-forming factories. By measuring the distances and ages of Cepheids throughout the disk, we can create a three-dimensional map of recent galactic construction, pinpointing where and when waves of star formation have swept through the galaxy over the past few 100 million years. This chronological power allows us to do more than just map space. It allows us to build a timeline. By combining the distances measured by these stellar clocks with their ages and chemical compositions, astronomers can assemble a coherent history of galactic events. We can determine the sequence of spiral arm formation, date past interactions with satellite galaxies, and understand how the rate of star formation has changed over billions of years. The rhythmic pulsations of these stars provide the steady tick of a cosmic metronome, giving us the temporal framework upon which the entire story of galactic evolution is hung. While the orderly orbits of stars and the tight-knit families of star clusters tell one part of the galactic story, there is another, more ghostly structure that paints an even more dramatic picture of a galaxy's violent past. These are the stellar streams, vast rivers of stars that flow through the halo of a galaxy like our Milky Way, often spanning hundreds of thousands of light years across the sky. They are not random collections. They are the lingering, dissolving remains of dwarf galaxies or globular clusters that ventured too close to the immense gravitational pull of their giant host. Over billions of years, the overwhelming tidal forces of the larger galaxy have physically torn these smaller systems apart, stretching them out into long, thin arcs that trace the precise path of their orbital death spiral. The stars within these streams are cosmic refugees, and they carry with them the indelible memory of their extragalactic origins, a story written in their chemistry and their motion that is completely distinct from the native-born stars of the galaxy they now call home. The most famous and extensive example of this is the Sagittarius Stream, a colossal ribbon of stars that wraps around the entire Milky Way. This stream is all that remains of the Sagittarius dwarf elliptical galaxy, a small satellite galaxy that our Milky Way has been in the process of devouring for the last several billion years. As this dwarf galaxy was pulled into repeated close encounters, our galaxy's gravity acted like a cosmic cheese grater, systematically stripping away its stars with each pass. The stars that were torn loose were flung into elongated orbits, forming the immense stream we see today, while the dwarf's dense core continues its slow-motion disintegration. The evidence for its foreign origin is undeniable. The stars in the Sagittarius Stream have a distinct chemical signature. They are, on average, more metal-poor than the stars in the Milky Way's disk, a telltale sign that they formed in a smaller, less evolved system. Their kinematics are also a dead giveaway, as they move together on a coherent yet tragic path that is completely different from the placid rotation of the galactic disk. They are a population of outsiders, their very presence a permanent monument to a single act of galactic cannibalism. But these streams are more than just historical records. They are active scientific tools that allow us to probe the most mysterious component of our galaxy, its dark matter halo. We cannot see dark matter directly, but we can map its distribution by observing how its gravity influences the things we can see, and stellar streams are perhaps the most sensitive instruments for this task. The precise shape, density, and path of a stellar stream are exquisitely sensitive to the gravitational tugs and pulls of the dark matter halo it orbits through. Any kinks, gaps, or wrinkles in a stream are like fingerprints left by past interactions with dark matter subhalos or disturbances in the overall gravitational field. A perfect example of this is the GD1 stream, an incredibly thin and long structure that is considered one of the most pristine stellar streams ever discovered. Its very existence and smoothness tell us that it has been orbiting for a very long time in a relatively quiet region of the halo. However, detailed observations have revealed a few peculiar gaps and a slight wobble in its structure. Astronomers believe these features could be the scars of a past collision with a clump of dark matter, a direct and observable effect of the invisible scaffolding that shapes our entire galaxy. By studying these subtle distortions, we can effectively perform a galactic CT scan, using the stream as a tracer to determine the total mass, the shape, and even the lumpiness of the Milky Way's dark matter halo. These great cosmic scars, these rivers of stolen stars, provide the most direct and visceral evidence for the theory of hierarchical galaxy formation. This is the fundamental idea that large galaxies like our Milky Way were not born in their current majestic forms. Instead, they were assembled over billions of years through a relentless process of attracting, colliding with, and ultimately digesting smaller galaxies. Every stellar stream is a fossilized remnant of this process, a half-digested meal still visible in the galactic belly. They show us that galaxy growth is not a gentle, steady accretion of gas, but a violent, messy, and dramatic history of conquest and consumption. The serene beauty of a spiral galaxy's disk with its elegant arms hides a ferocious past written in the faint, flowing scripts of these stellar streams. They are the ultimate proof that our galaxy is a dynamic, evolving entity, one that is still growing and changing today, with the ghosts of its past meals forever circling in the darkness beyond the light of its spiral arms. So far, we've seen how stars remember the chemistry and violence of their birth, but this cosmic memory extends far beyond the star itself. It directly shapes the very possibility of planets and life. When we look at a star with a planetary system, we are not just looking at a sun with orbiting rocks. We are looking at a product of its galactic environment, a celestial family whose existence, architecture, and potential for habitability were profoundly influenced by the conditions of the neighborhood it was born in. This memory is written in two powerful ways. First, in the fundamental recipe of the star and its planets, and second, in the dynamic stability of the system over billions of years. The most direct link between a star's memory and its planets is its chemical composition, specifically its metallicity. You see, planets, especially the giant gas planets like Jupiter and Saturn, don't just appear, they have to be built. The core accretion model of planet formation tells us that a giant planet begins as a tiny seed, a rocky, icy planetary core massive enough to start gravitationally pulling in vast amounts of hydrogen and helium gas from the surrounding protoplanetary disk. The crucial building blocks for that initial seed are the metals, all the elements heavier than hydrogen and helium. These are the rocks, the ices, the dust grains. A star born from a cloud that is rich in these metals, a cloud that has been generously fertilized by generations of prior supernovae, has a tremendous head start. It is formed from a disk that is simply packed with more planetary construction material. This is why astronomers discovered a very clear and powerful correlation. Stars with higher metallicity are significantly more likely to host giant planets. It's a simple case of supply and demand. More raw materials mean a much higher chance of successfully building those massive planetary cores before the young star's radiation blows the leftover gas away. A perfect example of this is the spectacular HR 8799 system, a young star located over 130 light-years away. This star is not just metal-rich, it's a veritable cosmic refinery, and orbiting it are 4 giant planets, each several times the mass of Jupiter, all directly imaged dancing around their parent sun. This entire extravagant system is a direct result of its enriched birth environment, a testament to the fact that the galactic history of chemical enrichment doesn't just change stars, it enables the formation of entire solar systems on a grand scale. But the galactic influence doesn't stop at the construction phase. It also plays a critical role in the long-term survival of these newborn worlds. A star's location within its galaxy determines the density of its stellar neighborhood, and this density has dramatic consequences for planetary stability. Imagine a young planetary system forming in a serene, quiet suburb of the galaxy, far from the crowded urban core. Here, the distances between stars are vast, and close encounters are incredibly rare over billions of years. This peaceful environment allows planets to settle into stable, orderly orbits, providing the calm and consistency that may be necessary for the delicate processes of life to emerge and evolve. Our own solar system, orbiting in a relatively quiet region of the Milky Way's Orion arm, likely benefited from this kind of galactic peace. Now, contrast that with a star born in a dense stellar cluster near the galactic center, or in a bustling hub like a globular cluster. This is a chaotic, urban environment where stars are packed together much more tightly. In such a crowded place, the gentle gravitational dance of a young planetary system is constantly threatened. A close pass by another star, even a distant one, can act like a gravitational bull in a china shop. Such an encounter can violently yank planets from their stable orbits, flinging them into the cold depths of interstellar space or sending them careening inward to be consumed by their own star. It can warp and tilt entire planetary disks, creating bizarre, highly eccentric orbits that would make any world uninhabitable. For a planet that might have once been in a temperate, Goldilocks zone, such a gravitational perturbation could be a death sentence, triggering eons of orbital chaos and extreme climate swings. Therefore, a star that retains a rich system of planets on stable, circular orbits is telling us a story not just about its birth cloud's chemistry, but also about its peaceful life in a sparsely populated galactic neighborhood, safe from the gravitational turmoil that defines more crowded regions. By studying the thousands of exoplanet host stars we've now discovered, astronomers are beginning to piece together a galactic map of planet formation and habitability. We can start to ask profound questions. Are certain regions of a galaxy, like the metal-rich inner disk, better at producing giant planets, while the quieter outer suburbs might be more conducive to smaller, rocky worlds? Does the violent environment near the galactic center, with its frequent supernova and stellar interactions, actively sterilize regions of potential habitability even if planets can form? Each exoplanetary system we characterize adds a data point to this grand puzzle, allowing us to infer the galactic history of not just star formation, but of planet formation and the distribution of the raw ingredients for life itself. The memory carried by a star with planets is therefore one of the most complex and poignant. It's a story of having just the right ingredients in just the right place at just the right time to build a stable home in the cosmos. Just as an individual's life story is shaped by the culture and environment they grow up in, a star's memory is profoundly influenced by the specific type of galaxy it calls home. The grand architectural design of a galaxy, its morphology, isn't just a pretty shape, it's the direct result of its entire violent and dynamic history, and that history is permanently stamped onto the chemical and physical properties of every single star within it. A spiral galaxy, an elliptical giant, and a chaotic irregular dwarf each provide a completely different setting for stellar birth and life, and the stars that form there become living archives of those distinct cosmic lifestyles. Let's start with the spirals, the grand pinwheels of the universe, like our own Milky Way and our neighboring Andromeda galaxy. These galaxies are the bustling, vibrant cosmic cities, characterized by ongoing construction and a clear division of neighborhoods. This structure creates a rich and layered stellar memory. In the bright, star-filled disk, particularly within the spiral arms, we find the vibrant, young stellar populations. These are the metal-rich stars, born from gas clouds that have been continuously recycled and enriched by countless supernovae over billions of years. Their high metallicity is a memory of the galaxy's long and productive history of star formation. Our Sun is a perfect citizen of this disk, its composition a testament to this sustained enrichment. But venture out of the disk and into the surrounding halo, and you find a completely different story. Here, the stars are ancient, lonely, and extremely metal-poor. These old relics remember a far wilder and more primitive time, the galaxy's violent youth, when it was first assembling itself and had yet to establish its orderly disk. This stark contrast between the young, metal-rich disk and the old, metal-poor halo is the defining chemical signature of a spiral galaxy, a memory of a past era of chaotic formation that eventually settled down into a stable, star-making factory. But even within this spiral structure, the details matter. Take the Andromeda Galaxy's central bulge. Recent observations show that its stars are not all the same age. Instead, they reveal a mix of populations. Some are very old, but others are surprisingly young. This is not what you'd expect from a simple, quiet formation history. This mixed signal is a powerful memory, a chemical fossil record pointing to a dramatic past. Astronomers now believe this complexity is the result of a major merger, a colossal collision with another galaxy that occurred billions of years ago. That violent event would have funneled huge amounts of gas into the center, triggering a burst of new star formation that was literally imprinted onto the existing older population. So, the stars in Andromeda's bulge carry a dual memory, one of the galaxy's earliest days and another of its most catastrophic and transformative event. Now contrast this with the elliptical galaxies. These are the featureless, reddish, football-shaped giants that often dominate the centers of galaxy clusters. If a spiral galaxy is a bustling metropolis, an elliptical is a quiet retirement community, or perhaps the silent aftermath of a cosmic battlefield, their smooth, amorphous shape is itself a memory. It is the classic signature of a system that has undergone a ferocious merger. When two large spiral galaxies collide, their beautiful disks are utterly destroyed in the gravitational chaos. The orderly orbits of their stars are scrambled into a random, buzzing swarm, erasing all traces of spiral structure. Furthermore, the collision drives vast amounts of gas into the galactic center, fueling an immense burst of star formation that quickly consumes all the available fuel. The result is a galaxy composed overwhelmingly of old, red stars. But here's the fascinating twist. These stars are often very metal-rich. This is a crucial memory. It tells us that the spiral galaxies that merged to form this elliptical were themselves mature and already highly enriched. The collision didn't just create an old population, it locked in the chemical wealth of its progenitors. The stars in an elliptical galaxy remember not one but two lives, their first life in a stable spiral disk and their second life, reshuffled and aging together in the merged remnant. The lack of gas and ongoing star formation means that stellar memory in an elliptical is essentially frozen in time after that last major event. It tells a story of a dramatic climax followed by eons of quiet aging. Finally, we have the irregular galaxies. These are the cosmic bohemians, the small, misshapen, and often chaotic-looking systems that lack any defined structure. They are typically small, low mass, and often companions to larger galaxies. Their very irregularity is a key part of their story. Many are irregular precisely because they are being gravitationally twisted and distorted by a massive neighbor. Their shape is a memory of ongoing tidal harassment. This interaction has profound effects on their stellar populations. It can compress gas clouds, triggering intense but short-lived bursts of star formation. This means an irregular galaxy might contain spectacular, bright blue clusters of newborn, massive stars right alongside much older, redder populations. The chemical signatures in these stars can be incredibly diverse. One region might show the pristine, low metallicity composition of the galaxy's original gas, while another region, enriched by the sudden death of massive stars from a recent burst, could have much higher metal content. The stars in an irregular galaxy remember a life of turbulence and drama, of external forces dictating their formation history in sudden, violent fits and starts rather than a steady, settled progression. They are living records of a galaxy that has never found peace, constantly being stirred and shaken by its environment. By reading these morphological signatures, the clear divisions in a spiral, the homogeneous aging of an ellipse, and the chaotic diversity of an irregular, We can classify galaxies not just by how they look today, but by the entire epic story of their formation and evolution, a story written in the collective memory of their billions of stellar inhabitants. We have explored the profound memories stars carry of the chemical and dynamic histories written by visible matter, but there is an invisible hand that guides this entire cosmic narrative, a ghostly architect whose presence is felt only through its immense gravitational pull. This is the mysterious realm of dark matter, a substance that does not emit, absorb, or reflect any light, yet it is the single most important factor in building the very galaxies that stars call home. And while dark matter itself is invisible, the stars remember its influence with absolute clarity, their very existence, their motions, and their distribution acting as a permanent testament to the unseen halo that cradles them. To understand this invisible partnership, we must first picture a galaxy not as a simple disk of stars, but as an immense sphere of dark matter, a cosmic egg whose gravitational yoke is far larger and more massive than the visible eggshell of stars and gas we can see. This dark matter halo forms first, its gravity providing the essential scaffolding that attracts ordinary atoms of hydrogen and helium. Without this dark matter foundation, galaxies as we know them simply could not form. The gravity from visible matter alone is far too weak to hold onto gas long enough for it to collapse and fragment into stars. Simulations of the universe without dark matter show a pathetic and empty cosmos. The gas just drifts apart, never coalescing into the magnificent structures we observe. The very ability of a galaxy to gather and retain the raw material for star formation is a direct gift from its dark matter halo. So every star that has ever shone is, in a very real sense, a child of dark matter. Its existence is the first and most fundamental memory of this unseen force. But the influence of dark matter is far more nuanced than just providing a gravitational well. Its specific distribution sculpts the types of stars that form and where they can live. This is dramatically evident in the smallest galaxies, the dwarf spheroidals that orbit giants like our Milky Way. These tiny galaxies are utterly dominated by dark matter. It makes up over 99% of their mass. This might sound like it would make them ideal star factories, but the opposite is true. This overwhelming dark matter dominance actually suppresses star formation. Here's why. The dark matter forms a vast diffuse halo. The ordinary matter, the gas, falls into the center of this halo, but it has nothing to collide with to lose energy and collapse further. There's not enough other gas to create the friction needed, so the gas just sits there, unable to condense into dense clouds that could ignite new stars. This is why many of these dwarf galaxies contain only a single, ancient population of stars, a brief burst of formation in the early universe before the dark matter put a stop to it. The old, metal-poor stars in these dwarfs are a direct memory of an environment where dark matter's grip was so total that it strangled further galactic evolution, freezing these systems in time. Conversely, the most powerful tool we have for mapping the invisible dark matter halo of our own Milky Way comes from the tragic stories of other galaxies it has consumed. We discussed stellar streams, those beautiful rivers of stars that are the torn-apart remains of dwarf galaxies and clusters. These streams are more than just historical records. They are the most sensitive gravitational probes we have. As a stream of stars orbits through the Milky Way's halo, its shape and density are exquisitely sensitive to the gravitational tugs from both visible matter and, more importantly, the invisible dark matter. Think of a stream as a delicate necklace of pearls. If the gravitational field of the halo were perfectly smooth and symmetrical, the necklace would remain a smooth, symmetrical arc. But if the dark matter halo has lumps and subhalos, smaller clumps of dark matter within the larger halo, their gravity will tug on the stream, creating gaps, kinks, and wrinkles in the stellar necklace. By meticulously measuring the precise positions and motions of stars in streams like GD1, astronomers are effectively performing a galactic ultrasound, using these visible tracers to map the invisible structure of the dark matter that comprises over 90% of our galaxy's mass. Every subtle warp in a stream is a memory of a gravitational interaction with the unseen. Finally, the very motions of stars themselves betray the presence of this dark matter. When astronomers measure the orbital velocities of stars within a galaxy, they make a startling discovery. According to the laws of gravity and the amount of visible mass we can see, stars on the outskirts of a spiral galaxy should be moving much more slowly, like planets in our solar system that orbit more sluggishly the farther they are from the Sun. But that's not what happens. Instead, the orbital speed of stars remains constant far out into the distant, dark reaches of the galactic halo. This flat rotation curve is one of the strongest pieces of evidence for dark matter. It tells us that there is a huge amount of mass that we cannot see, mass that extends far beyond the visible edge of the galaxy, whose gravity is whipping those outer stars around at unexpectedly high speeds. The kinematics of every single star in the outer disk is a data point, a silent witness to the immense, invisible mass that holds the entire galaxy together. So, while we cannot see dark matter directly, the stars act as countless informants, their positions and motions painting a detailed portrait of the hidden architect that has shaped their home from the very beginning, setting the gravitational stage upon which all the subsequent drama of stellar life, death, and feedback would play out. As we've traced the gravitational influence of dark matter, we've seen how it provides the stage for galaxy formation. But it's the stars themselves that become the dynamic actors, capable of reshaping their own environment in a powerful process known as feedback. This is a memory not just of conditions, but of action and consequence, a stellar generation leaving an indelible mark on the next. Massive stars are the titans of this cosmic drama, living short, violent lives that end in spectacular supernovae. But even before that final cataclysm, they are ceaselessly reshaping their surroundings through the relentless force of their stellar winds. Imagine a star dozens of times more massive than our Sun, burning at such a ferocious rate that its outer layers are literally blown away into space by the intense pressure of its own radiation. These are not gentle breezes, they are hurricane-force gales of charged particles and energy that stream outwards at millions of miles per hour, carving vast cavities in the surrounding interstellar gas and dust. This constant outflow acts like a cosmic plow, pushing material into dense shells that can later collapse to form new stars, while simultaneously evacuating other regions and effectively shutting down star formation by dispersing the essential raw materials. The supernova explosion that inevitably follows is merely the grand finale, a titanic shockwave that injects the newly forged heavy elements and a colossal amount of kinetic energy back into the galactic ecosystem. This cycle of life, death, and rebirth is a fundamental feedback loop, a self-regulating mechanism that governs the pace of a galaxy's evolution. Nowhere is this process more extreme and visibly dramatic than in a starburst galaxy like the famous M82, the Cigar Galaxy. Here, star formation has been whipped into an absolute frenzy, likely triggered by a close gravitational encounter with its larger neighbor, M81. In the core of M82, stars are being born at a rate more than 10 times faster than in our entire Milky Way galaxy. This creates an environment of unimaginable intensity, where the combined stellar winds and the relentless shock waves from frequent supernova generate a superheated, pressurized environment. This energy has to go somewhere, and it does so in the most spectacular way possible. It blasts out of the galaxy in a colossal bipolar outflow, a galactic wind that stretches for tens of thousands of light years. The Hubble Space Telescope has captured stunning images of this fiery tempest, a roiling plume of hot gas and dust superheated to millions of degrees and heavily enriched with carbon, oxygen, and iron, the elemental ashes of all those short-lived massive stars. This wind is a primary delivery mechanism, a way for a galaxy to export its hard-won metals out of the star-forming disk and into the vast, lonely reaches of the circumgalactic medium, the sparse halo of gas that surrounds a galaxy. This process enriches not just the immediate environment but the entire future reservoir of gas from which subsequent generations of stars and even entire galaxies may one day form. The specific chemical signature found in the stars that eventually form from this enriched halo will forever remember this violent, explosive chapter in their galaxy's history. While the massive stars dominate the feedback process with their spectacular exits, we must not overlook the quiet, persistent contribution of the countless low-mass stars like our own Sun. Their role is more subtle but no less crucial over the long span of cosmic time. For the vast majority of their lives, these stars are stable and steady, but they too have a final act of recycling. In their old age, as they evolve into red giants and later into planetary nebulae, they gently shed their outer layers back into space. This isn't a violent explosion but a more graceful release, a slow exhalation of material that has been processed through nuclear fusion in their cores. This returned material is rich in specific lighter elements like carbon, nitrogen, and a significant amount of helium, the primary products of the stable hydrogen and helium burning that powers such stars for billions of years. A planetary nebula with its beautiful, intricate shapes is the visible signpost of this gentle feedback. The famous Ring Nebula, for instance, is not just a gorgeous cosmic flower. It is a delivery of newly minted carbon and other elements, a nutrient infusion into the interstellar medium that will one day be incorporated into future stars, planets, and perhaps even life. This constant background trickle of enriched material from low-mass stars works in concert with the violent injections from massive stars, creating a complex chemical tapestry over time. By studying the collective properties of stellar populations across different types of galaxies, astronomers can read the history of these feedback loops. A galaxy with a very old stellar population and little current star formation is likely one where early, intense feedback from the first massive stars effectively blew out or heated up most of the remaining gas, quenching further activity and leaving the galaxy to age quietly. A galaxy like our Milky Way, with a mix of old and young stars, represents a more balanced, regulated cycle of feedback where star formation proceeds in fits and starts, modulated by these processes. And a starburst galaxy like M82 shows us feedback in its most extreme, unregulated form, a spectacular but ultimately unsustainable burst of creation that will likely consume its available fuel and then fade. The specific elemental patterns we see in stars, the balance between elements made in slow, stable burning and those forged in rapid, violent explosions, are the direct result of the efficiency and nature of these feedback processes in their birth environment. This intricate dance between creation and destruction, between the energy that compresses gas and the energy that disperses it, is what ultimately sculpts the evolution of galaxies from their vibrant, chaotic beginnings to their quiet, aging futures, with every star acting as a permanent chemical record of how that balance was struck. While the powerful winds and explosive deaths of stars provide one method of enriching the galactic environment, there is another, more subtle and pervasive agent of change constantly zipping through the void at nearly the speed of light. These are cosmic rays, not rays of light at all, but atomic nuclei, mostly protons, that have been accelerated to unimaginable energies. They are the universe's natural particle accelerators, and as they tear through clouds of interstellar gas, they leave behind a unique and lasting chemical signature, a high-energy memory that gets locked into the next generation of stars. This process doesn't create heavy elements. Instead, it forges a specific set of light, fragile elements that are difficult to make anywhere else, providing a crucial and often overlooked chapter in the story of galactic chemistry. The primary way cosmic rays alter the composition of the interstellar medium is through a violent process called spallation. Imagine a single proton, a cosmic ray, screaming through space and slamming directly into the nucleus of a sedentary atom, say a heavy element like carbon or oxygen that is just drifting peacefully in a gas cloud. The impact isn't a gentle nudge, it's a catastrophic collision. The tremendous energy of the cosmic ray shatters the larger nucleus into smaller, lighter fragments, much like a sledgehammer smashing a rock into gravel. These fragments are the spallation products, and they are predominantly the light elements lithium, beryllium, and boron. This is a vital piece of the cosmic puzzle because these three elements are notoriously difficult to create through standard stellar nucleosynthesis. The intense heat inside stars quickly destroys them, and they are not produced in significant quantities in the Big Bang or in most supernovae. Therefore, their primary cosmic source is this relentless bombardment by high-energy particles. The abundance of lithium, beryllium, and boron in a region of space acts as a direct gauge, a cosmic dosimeter measuring the historical flux of cosmic rays that have passed through it. When a new star then forms from a gas cloud that has been subjected to this intense cosmic ray bombardment, it inherits this distinct chemical signature. Its atmosphere will be slightly but detectably enriched in these specific light elements compared to stars that formed in more quiescent, shielded regions. A perfect example of this is the star known as HD 84937, an ancient star residing in the halo of our Milky Way. Spectral analysis of this star reveals a curious anomaly. It possesses a significantly higher abundance of lithium than most other stars of its similar old age and low metallicity. This is a telltale clue, a chemical fossil pointing directly to the conditions of its birth environment billions of years ago. The most plausible explanation is that the primordial cloud that collapsed to form HD 84937 was itself bathed in a strong flux of cosmic rays, likely generated by nearby supernova that exploded just before or during its formation. The cosmic rays spalled heavier nuclei in the cloud, producing extra lithium that was then woven into the fabric of the newborn star. Its enhanced lithium level is a permanent memory of that high-energy nursery. By studying the abundances of these spallation elements in different stellar populations, astronomers can reconstruct the history and intensity of cosmic ray activity throughout the galaxy's evolution. This provides a unique window into the energy budget of our galaxy and the powerful particle acceleration mechanisms at work. The primary factories for these high-energy particles are the shock waves from supernova remnants. As a colossal blast wave from a stellar death expands outwards, it can act like a natural cyclotron, trapping charged particles and whipping them around in the tangled magnetic fields at the shock front, accelerating them to near-light speeds over vast distances. The efficiency of this process dictates how many cosmic rays are produced and how much lithium, beryllium, and boron are subsequently forged. By measuring the levels of these elements in stars of different ages, we can effectively trace how the power of galactic cosmic ray accelerators has changed over billions of years. Were they more efficient in the crowded, violent early galaxy, or has their output remained relatively constant? The answers are written in the subtle spectral lines of these fragile elements, a high-energy message from the past that helps us understand one of the most dynamic and energetic processes shaping the interstellar medium from which every star is born. While the violent energy of supernova and the relentless rain of cosmic rays shape the galactic environment in dramatic ways, there is another, far more subtle force weaving through the cosmos, one that provides an invisible architecture, a silent scaffold that guides the very birth of stars. This is the influence of galactic magnetic fields. Though we cannot see them directly, these fields are woven into the fabric of space, and they leave a profound and lasting memory on every star that forms within their influence. They are the ghostly cartographers of star formation, mapping out the flows of gas and dust, sometimes resisting the pull of gravity and other times channeling it into precise, elegant structures. The story of a star's birth is not just one of chaotic collapse, but also of a delicate dance with these pervasive magnetic forces. To understand their role, imagine a vast, dark cloud of molecular gas, a stellar nursery adrift in the galactic disk. Gravity wants to pull this cloud inward, to crush it into a dense knot that will eventually ignite as a new star. But the magnetic field threaded through that cloud pushes back. The field is created by the movement of charged particles within the gas, and it acts like a network of incredibly fine, invisible springs. These magnetic field lines provide pressure, a form of support that can effectively prop up the cloud against its own weight, slowing down the collapse and delaying the moment of star birth. This magnetic support is a crucial regulatory mechanism throughout the galaxy. It prevents all of the gas from collapsing into stars at once, effectively stretching out the star formation process over billions of years and ensuring a steady, sustainable pace of stellar creation rather than a single, brief, and furious burst. But these fields are more than just a simple break on gravity. They are also master sculptors. Instead of a cloud collapsing into a simple sphere, the magnetic field can guide the flow of material, channeling it along the invisible field lines. This process is what creates the magnificent filamentary structures we see in great nebulae like Orion. The gas doesn't fall in randomly. It flows like iron filings aligning to a magnet, forming long, river-like tendrils of dense material. It is within these magnetically defined filaments that the densest cores form, the eventual seeds of protostars. Observations from powerful radio telescopes and instruments like the Stratospheric Observatory for Infrared Astronomy, or SOFIA, have given a stunning confirmation of this. In the Orion molecular cloud, one of our closest stellar nurseries, we can now actually map the magnetic field orientation by measuring the polarization of light from dust grains. These tiny grains align themselves perpendicular to the local magnetic field, and the polarized light they emit acts like a compass, tracing out the field's structure. These observations show a remarkably ordered magnetic field geometry, with field lines running along the length of the famous integral-shaped filament, directly guiding the flow of material and influencing whether newborn stars, still nestled in their cocoons of gas, will ultimately form. This magnetic guidance system doesn't just shape the nursery, it leaves a permanent imprint on the stars themselves. A key memory of this influence can be found in the rotation of a newborn star. As a cloud collapses, it conserves its original tiny amount of spin, speeding up dramatically as it shrinks the same way an ice skater spins faster when they pull their arms in. This should create a star spinning furiously, but most young stars rotate at a much more moderate pace. The primary brake on this spin is thought to be the magnetic field. The young star, with its own strong magnetic field, connects to the magnetic field of its surrounding disk. This creates a powerful magnetic brake, effectively transferring the star's angular momentum out into the disk and slowing its rotation. The final spin rate of a star is therefore a memory of the strength and configuration of the magnetic fields during its infancy. Furthermore, the magnetic field imprints itself on the very light the star emits. The field can polarize the light coming from the star's surface or from the dust around it, and by carefully measuring this polarization, we can deduce the strength and orientation of the field that was present at its birth. These are subtle signatures, but they are a direct, fossilized record of the invisible forces that midwifed the star into existence. These magnetic fields that weave through star-forming clouds are not fleeting phenomena. They are themselves fossils, relics of the larger-scale dynamics of the galaxy itself. The magnetic field of the entire Milky Way is thought to have been generated and amplified over billions of years by a dynamo effect, driven by the rotation and turbulent motions of the galaxy's ionized gas. The field we measure today in a nearby nebula is a complex tapestry, woven from the primordial field that existed in the early universe and then twisted and shaped by eons of galactic rotation, shear, and the explosive feedback from countless supernovae. The strength and orientation of the field in any given location is thus a product of that region's history. A strong, ordered field in a quiet region of the disk might be a pristine remnant of an earlier Comet era. A chaotic, tangled field near a recent supernova remnant tells a story of violent disruption. By reading the magnetic memories in young stars, we are also indirectly reading the history of the galactic magnetic field itself, understanding how this fundamental but invisible component of a galaxy evolves and influences its evolution. This hidden framework is a critical piece of the puzzle, explaining the diversity of stellar systems and the efficiency with which gas is transformed into the brilliant suns that light up the darkness. While the quiet, steady influence of magnetic fields provides an unseen structure for star birth, the galaxy is also a stage for far more violent and dramatic gravitational performances, events so powerful they can tear galaxies apart and reshape them in their entirety. This is the realm of tidal interactions, where the immense gravitational pull of one galaxy literally stretches and distorts another, leaving permanent scars not just in the shapes of the galaxies involved, but in the very life stories of the stars within them. It's a process of cosmic sculpting, where gravity acts as both a destructive and creative force, and the stars that endure these encounters become living records of the gravitational drama they witnessed. The most spectacular and visible evidence of these titanic clashes are the vast, graceful arcs of stars known as tidal tails. These are not random structures. They are the direct result of a close gravitational encounter between two galaxies, an event that unfolds over hundreds of millions of years. As two galaxies pass near each other, their mutual gravity creates a tremendous tidal force, the same kind of force the Moon exerts on Earth's oceans, but on an unimaginably colossal scale. The difference in gravitational pull on the near and far sides of each galaxy is so extreme that it overcomes the gravity holding the galaxies together, pulling long streams of stars, gas, and dust out into intergalactic space. The iconic antennae galaxies are perhaps the most famous example of this process in action. In stunning telescopic images, we see two spiral galaxies locked in a slow-motion collision, with two enormous, curved tails of material flowing out from them like the antennae of some gigantic insect. The stars within these tails are refugees, violently ripped from their home galaxies and flung into the void. Their kinematics are chaotic, their motions telling a story of a sudden and traumatic gravitational encounter. Furthermore, their star formation histories are often abruptly truncated. The gas that was once their potential future was stripped away in the encounter, leaving behind a population of stars that will age in isolation, their development frozen at the moment of the collision. These tidal tales are not just beautiful, they are fossilized records of the precise trajectories, speeds, and masses of the galaxies involved, allowing astronomers to rewind the clock and reconstruct the entire event. But tidal forces don't just create beautiful streams, they also have a profound and contrasting effect on the dwarf galaxies that orbit massive hosts like the Milky Way. For these smaller systems, a close encounter with a giant can be a transformative experience, either triggering a fiery burst of new life or snuffing out their potential entirely. This tidal triggering is a fascinating paradox of gravity. As a dwarf galaxy is stretched and compressed by the tidal forces of its large neighbor, the gas clouds within it can be violently shaken. This compression can overwhelm the internal pressure that supports those clouds against collapse, triggering a sudden, intense wave of star formation, a starburst. It's the cosmic equivalent of squeezing a sponge and watching water gush out. The gravitational squeeze forces the gas to collapse and ignite into new stars at a ferocious rate. We see evidence of this in several dwarf satellite galaxies of the Milky Way. Conversely, the same tidal forces can have the exact opposite effect, leading to a process called tidal quenching. If the interaction is particularly violent or prolonged, the tidal pull can actually strip the dwarf galaxy of its gas reservoir entirely. Without this cold, dense gas, the raw fuel for star formation, the galaxy's ability to make new stars is completely shut down. It becomes a fossil system filled with an aging population of stars that will slowly redden and fade over billions of years, its evolutionary story brought to an abrupt and premature end. The fate of a dwarf galaxy in this situation, whether it experiences a burst of life or a slow death, depends on a delicate balance: the strength of the tidal force, the angle of the encounter, and the amount of gas the dwarf had to begin with. A magnificent and close-up laboratory for studying these tidal effects is right in our own cosmic backyard with the Magellanic Clouds, the two largest dwarf galaxies orbiting the Milky Way. For a long time, their prolific star formation, especially in the large Magellanic Cloud, was a puzzle. These are small galaxies, and they should have used up their gas long ago. The answer lies in their gravitational dance with our galaxy. As the clouds orbit the Milky Way and as they interact with each other, they experience immense tidal forces. These forces compress the vast reservoirs of gas within them, and this compression is the direct trigger for the spectacular star-forming regions they contain, like the titanic Tarantula Nebula in the Large Magellanic Cloud, the most active starburst region in our entire local group of galaxies. Furthermore, the gravitational tug-of-war has pulled a vast stream of gas from these galaxies, known as the Magellanic Stream, which stretches across the southern sky. This stream is a clear testament to the Milky Way's gravitational influence, a ribbon of stolen material that will eventually fall into our galaxy, providing fresh fuel for future generations of stars. The vibrant stellar populations of the Magellanic Clouds are therefore a direct product of their interaction with us. Their star formation is not just internal, but tidally induced, an ongoing memory of their dynamic relationship with a giant neighbor. The gravitational repercussions of these interactions can extend beyond just reshaping stars and gas. They can reach right into the very heart of a galaxy and awaken a sleeping monster. The immense tidal forces generated during a galactic collision, can funnel vast quantities of gas and dust directly into the central regions of the galaxies involved. When this happens, it doesn't just create a burst of regular star formation. It can also feed the supermassive black hole that lurks at the galaxy's center. As this material spirals down into the black hole's accretion disk, it is heated to incredible temperatures, releasing a phenomenal amount of energy across the entire electromagnetic spectrum. This turns the galactic nucleus into an active galactic nucleus, or AN, one of the most luminous objects in the universe. The radiation and powerful jets erupting from this active core can then blast outwards, heating up or ejecting the remaining gas in the galaxy, and effectively shutting down star formation across the entire system. This means a tidal interaction can leave a dual memory, first, in the twisted shapes and tidal tails of the stars, and second, in the altered chemical and thermal state of the gas, heated by a black hole that was itself awakened by the gravitational encounter. This highlights a profound interconnectedness. Galaxies are not isolated islands. They exist in a complex web where a close encounter can set off a chain reaction that changes the destiny of the stars within them, triggers the birth of new suns, feeds central black holes, and ultimately writes a new chapter in the collective history of the local universe. But how do we actually read this cosmic calendar? How do we translate the steady glow of a star into a precise birth date billions of years in the past? This is where stellar archaeology becomes a rigorous science, employing ingenious techniques to tease out the age of a star, turning its light into a definitive timestamp for galactic history. Two primary methods allow us to do this: isochrone fitting and radioactive dating, each providing a unique and powerful way to listen to a star's memory of its own beginning. Let's start with isochrone fitting, a technique that is both elegant and deeply visual. The word isochrone itself means same time, and the method relies on a simple but profound fact. All the stars in a single cluster are born at essentially the same moment from the same cloud of gas. They are a stellar family, all the same age but with different masses. When astronomers plot these stars on a Hertzsprung-Russell diagram, a graph of their brightness versus their color or temperature, they don't scatter randomly. Instead, they fall along a beautifully clear, curved line. This line is the isochrone, and its precise shape is the key. A star's mass determines how quickly it burns through its nuclear fuel. High-mass stars are profligate, shining brilliantly but dying young. Low-mass stars are frugal, burning slowly for trillions of years. This means the exact point where a star of a given mass sits on that HR diagram curve changes predictably as it ages. By comparing the observed curve of a star cluster to a library of theoretical models, each model representing a different age, astronomers can find the perfect match. The model that fits the observed data best gives the age of the entire cluster. It's like having a set of identical twin children. You can tell their age by their height, their features, and their development all at once. A young cluster's isochrone will be dominated by bright, blue, massive stars still on the main sequence, while an ancient cluster's curve will show a sharp turn-off point where those massive stars have already ended their lives, leaving behind a population of cooler, redder stars. This powerful technique allows us to date entire populations of stars at once, providing firm anchor points in the galactic timeline. For individual stars, especially those not in clusters, astronomers turn to a more direct method, one that feels like something out of a geological textbook: radioactive dating. This technique uses the stars themselves as natural clocks by measuring the abundance of certain radioactive elements and their stable decay products in their atmospheres. The most famous cosmic clock is the decay of uranium-238 into lead-206. a process with a half-life of about 4.5 billion years, a time frame perfectly suited for measuring stellar ages. To use this clock, astronomers perform incredibly precise spectroscopy to detect the faint spectral signatures of these rare elements. For a star like our Sun, which has well-mixed layers, this gives a solid age estimate. But the true power of this method is for the oldest stars. Imagine measuring the amount of uranium and thorium in the ancient halo star HD 140,283, infamously nicknamed the Methuselah star. Its atmosphere contains only tiny, trace amounts of these heavy elements, but by measuring the ratio between the radioactive parent and the stable daughter elements, astronomers can calculate how long that radioactive material has been decaying inside the star. This is how we know that HD 140,283 is astonishingly ancient, with an age calculated to be over 13 billion years. This isn't just an old star, it's a relic that places a firm lower limit on the age of the universe itself. It had to form after the Big Bang, so its incredible age forces our cosmological models to account for a universe that is old enough to have created it. This single stellar memory is a fundamental constraint on our understanding of everything. By applying these dating techniques to stars across the Milky Way, we can begin to assemble a grand chronological narrative of our galaxy's life. We can construct what's known as an age-metallicity relation, a graph that plots a star's age against its metal content. This simple plot tells a complex story. In general, it shows a clear trend. The older a star is, the lower its metallicity tends to be. This makes perfect sense and confirms our understanding of galactic chemical evolution. The early universe had not yet been polluted by generations of supernovae, so stars born then were metal-poor. As time went on, the interstellar medium became richer, so younger stars were born with more metals. But the real power of this relation is in the details, the outliers and the groupings that reveal specific chapters of our galaxy's history. A perfect example of this is the story of the Milky Way's disk. It's not a single structure but a double-layered one, consisting of a thin disk and a thick disk. The age-metallicity relation reveals a stark difference between them. Stars in the thin disk, like our Sun, show a wide range of ages but are generally younger and have a higher average metallicity. They represent the continuous, ongoing star formation in the galaxy's recent history. The thick disk stars, however, are a different population altogether. They are systematically older and more metal-poor. This is a crucial memory. It tells us that the thick disk represents an earlier, distinct phase of the Milky Way's formation, a period of rapid and likely more chaotic star formation that occurred over 10 billion years ago before the galaxy settled into its current, quieter state. The existence of this older thick disk is evidence of a turbulent youth, possibly triggered by a major merger like the Gaia-Enceladus impact, which stirred up the early disk and gave it its greater thickness. By dating stars, we are not just putting numbers on them. We are identifying distinct generations of stellar populations, each with its own story, and using them to reconstruct the sequence of events: the initial collapse, the merger events, the settling of the disk, that built the galaxy we see today. This ability to place galactic events in a true chronological order transforms our understanding from a static picture into a dynamic movie, with stellar ages providing the essential timestamps for every scene. But before that enriched gas can collapse to form a new star, it exists in a complex and dynamic state known as the interstellar medium, or ISM. This is not empty space. It is the cradle of stars, a diffuse and multifaceted reservoir of gas and dust that fills the vast gaps between them. And just as a child inherits traits from its parents and the environment it was raised in, the interstellar medium inherits and remembers the entire chemical history of the galaxy. It is the ultimate repository, the grand library where the cumulative enrichment from every past stellar generation is stored, mixed, and made available for the next cycle of creation. The composition of this medium at any given place and time is the single most important factor determining the properties of the stars that will be born from it, making it a direct and powerful recorder of galactic evolution. The interstellar medium is far from uniform. It's a patchwork of different phases, each with its own density, temperature, and story to tell. The most crucial for star formation are the cold, dense molecular clouds. These are the dark nebulae we see silhouetted against the Milky Way, colossal structures that can contain enough material to form thousands of stars. It is within these frigid, opaque cocoons that the magic of star birth begins, and the key ingredient they contain, beyond the hydrogen and helium, is dust. Interstellar dust grains, though microscopic, play an outsized role. They are primarily composed of silicates and carbon, particles forged in the atmospheres of aging stars and blasted into space by stellar winds and supernovae. The amount of dust in a cloud is a direct proxy for its metallicity, its overall richness in heavy elements. A cloud with a high dust content is telling us it has been seeded by many previous generations of stars. This dust is not just a passive tracer, it is an active participant in the star formation process. The dust grains provide surfaces for hydrogen molecules to form, and they are incredibly efficient at radiating away the heat generated during gravitational collapse. This cooling effect is vital. It allows the cloud to fragment and condense into ever denser cores that can eventually overcome their internal pressure and ignite as stars. Therefore, a dusty, metal-rich molecular cloud is a fertile ground, predisposed to giving birth to stars that themselves will be metal-rich and, as we've learned, more likely to form planetary systems. Conversely, a more diffuse, low-density cloud of atomic hydrogen presents a very different picture. This warmer, more transparent phase of the ISM has not yet condensed enough to form molecules or significant dust. Stars that form from such pristine material would be metal-poor, relics from an earlier time. We can see this stark environmental contrast by looking beyond our own galaxy to our small satellite, the Small Magellanic Cloud. This dwarf galaxy has a much lower overall metallicity than the Milky Way. Observations of its interstellar medium reveal a corresponding scarcity of dust grains. The molecular clouds that do form there are less effective at cooling and fragmentation. This fundamentally changes the star formation process, potentially leading to a different distribution of stellar masses and affecting the very efficiency with which new stars are born. The ISM in the Small Magellanic Cloud is a memory bank of its quieter, less evolved galactic history, a place where the processes of enrichment and recycling have not run as far as they have in our own more massive galaxy. Perhaps the most astonishing evidence of the interstellar medium's role as a galactic historian comes from a discovery not in the depths of space, but right here on our own planet. The isotope Iron-60 is radioactive with a half-life of 2.6 million years. This is a blink of an eye on cosmic timescales, and crucially, it is not naturally produced on Earth. Its presence can mean only one thing. It was forged in a nearby supernova and then transported here. Scientists searching through deep-sea sediments and lunar regolith have found precisely defined layers containing an enhanced abundance of Iron-60. By dating these layers, they have been able to pin down specific times in the past few million years when our solar system, as it journeyed through the galaxy, plowed through clouds of interstellar material that had recently been enriched by a stellar explosion. This isn't just theoretical, It's direct physical evidence that the local interstellar medium around us carries the specific isotopic fingerprints of recent and specific cosmic events. Our planet has literally archived these events in its geological record. This means the ISM is not a well-mixed soup. It can preserve localized pockets of enrichment from individual supernovae for millions of years, like distinct chapters in a book that haven't yet been fully blended into the whole story. When a new star forms, it will sample the composition of its local cloud, and if that cloud contains the debris from a recent supernova, that new star's atmosphere will bear the unmistakable isotopic signature of that event, a precise timestamp of the violent death that preceded its own birth. The interstellar medium is therefore both a reservoir and a messenger, a dynamic, evolving medium that carries within it the specific stories of individual stellar lives and deaths, ready to be passed on to the next generation. But the story of galactic enrichment doesn't end at the visible edges of a galaxy. The violent processes that forge new elements and the fierce energy that shapes stellar nurseries have a profound and far-reaching side effect, one that literally blows the galactic legacy out into the vast, empty spaces between galaxies. This is the phenomenon of galactic winds, titanic outflows of hot, enriched gas that act as cosmic exporters, carrying the chemical memories of their host galaxies on a journey into the intergalactic void. These winds are not gentle breezes, they are superheated tsunamis propelled by the combined fury of countless supernovae, and in the most extreme cases, the awesome power of a supermassive black hole feasting at the galaxy's core. When a region of a galaxy goes into a ferocious burst of star formation, the collective effect of all those stellar winds and subsequent supernova explosions creates an immense overpressure, like a pot boiling over. This energy has to go somewhere, and it forces its way out of the galaxy's disk, punching through its own gravitational pull and dragging along with it a torrent of gas that has been heavily seeded with newly forged metals. This outflowing wind becomes a delivery system on an epic scale, a mechanism for a galaxy to literally seed its surroundings with the elemental building blocks of future cosmic generations. We don't have to look far into the cosmos to find a stunning example of this process in action. The starburst galaxy M82, located about 12 million light-years away, is the quintessential laboratory for studying galactic winds. Its core is a maelstrom of star birth, churning out new stars at a rate more than 10 times that of our entire Milky Way. The combined energy from all these young, massive stars and their frequent cataclysmic deaths has ignited a superwind of truly biblical proportions. Observations from telescopes like the Chandra X-ray Observatory reveal a colossal, bipolar fountain of multimillion-degree gas erupting from the galaxy's center, stretching for tens of thousands of light-years into the circumgalactic medium. Spectroscopic analysis of this outflowing material confirms it is absolutely laden with heavy elements like oxygen, iron, and silicon, the unmistakable chemical signature of recent and prolific supernova activity. This isn't just a temporary event, it's a continuous, energetic polluting of the local intergalactic environment. The wind from M82 is a direct, observable example of a galaxy actively recycling its material not just internally, but externally, spraying its enriched contents out into a region of space where it might one day mix with pristine gas and form entirely new structures, perhaps even new dwarf galaxies or the next generation of stars within the local group. This process of galactic export solves a fascinating cosmic puzzle, the so-called metallicity flaw. Even the smallest, most isolated dwarf galaxies, which have had very few internal supernovae of their own, still show a baseline level of heavy elements. They are not completely pristine. For a long time, this was difficult to explain. How do these tiny, quiet systems become slightly enriched? The answer appears to be that they didn't do it themselves. They were polluted by their more active, massive neighbors. A large galaxy like M82 or our own Milky Way, through its powerful galactic winds, can eject enriched material that eventually travels across millions of light years of empty space. When this metal-bearing wind eventually encounters a small, passive dwarf galaxy or a remote cloud of primordial gas, it can mix with it, raising its metallicity before it even begins to form its first stars. A star born from this pre-polluted gas would therefore carry a chemical memory that is not its own. Its atmosphere would show an anomalous abundance of elements that is completely out of step with its local environment and its galaxy's quiet history. It would be a cosmic immigrant, its very composition a ghostly fingerprint from a faraway, more violent galaxy whose winds reached across the void to touch it long before it was born. The ultimate destination for this exported material is the largest structure in the universe, the cosmic web. This is the vast, filamentary network of dark matter that forms the skeleton of the cosmos, where galaxies cluster like glittering beads on invisible strings. The spaces between these filaments are not entirely empty. They are filled with a diffuse, hot gas known as the intergalactic medium. For decades, this medium was thought to be almost purely primordial, a relic of the Big Bang composed of hydrogen and helium. But incredibly sensitive observations have revealed that it, too, contains trace amounts of heavy elements like carbon, oxygen, and silicon. This is a monumental discovery. The only way these elements could have gotten there is through galactic winds, which have, over billions of years, been slowly but surely polluting the entire cosmic web with the recycled ashes of dead stars. This means that the material between galaxies is not pristine. It is a dilute soup of galactic memories. When future galaxies form from the condensation of this web, they will be born already pre-enriched, their earliest stars starting their lives with a chemical head start provided by the winds of long-dead galaxies from a previous cosmic epoch. This establishes a profound connectivity. No galaxy is an island. Each is linked to every other through these vast, invisible rivers of enriched material, each contributing its own unique chemical signature to the grand reservoir of the cosmos, ensuring that the memories of stellar lives are not lost but are instead shared across the universe, becoming part of a common inheritance for all that follows. So far, we've seen how a star's composition and motion tell a story of galactic history, but there's an even more fundamental blueprint that is set at the very moment of a star's birth, a blueprint that dictates not just its own destiny, but the future evolution of its entire galaxy. This is the initial mass function, or IMF, and it is one of the most profound yet subtle memories a stellar population carries. In simple terms, the IMF is the cosmic rulebook that governs how a giant cloud of gas partitions its mass when it fragments to form stars. Does it produce a few colossal behemoths and a multitude of tiny red dwarfs, or a balanced spread of medium-sized suns like our own? The answer to that question is not random. It is a direct and lasting memory of the precise physical conditions within that star-forming nursery, the cloud's temperature, its level of turbulence, and even the strength of its magnetic fields at the moment of collapse. This initial recipe for stellar masses then sets the course for everything that follows: how brightly the stellar family will shine, what kinds of elements it will forge, and how violently it will feed back energy into the galaxy to trigger or quench the next round of star formation. The classic, most common IMF we observe throughout the Milky Way's disk is a remarkably consistent pattern, one that seems to favor the small and faint. For every single massive star born with 10 times the mass of our Sun, that same cloud will form roughly 10 stars with solar-like masses and a staggering 50 lower mass red dwarfs. This is a bottom-heavy distribution, and it implies that the universe has a strong preference for manufacturing frugal, long-lived stars over the brilliant but profligate giants. This consistency is itself a clue. It suggests that the conditions in typical molecular clouds across our galaxy, the pressures, temperatures, and levels of turbulence fall within a fairly narrow range that reliably produces this same outcome. It's a standardized cosmic production line. However, when we look at extreme environments, the rulebook appears to be rewritten. The most compelling evidence for a variable IMF comes from the hearts of starburst galaxies and the intense, crowded regions near our own galactic center. In these places, star formation isn't a gentle process. It's a frantic, pressurized frenzy. Take the Arches cluster, for instance, one of the most spectacular stellar nurseries in our galaxy, located a mere 25,000 light-years from the supermassive black hole at the Milky Way's core. This cluster is a maelstrom of youth and density, packed with stars so close together that the environment is utterly unlike the serene suburb where our sun was born. When astronomers census the stars in the Arches cluster, they find a startlingly different mass distribution compared to a quiet cluster. It appears to be top-heavy, meaning a significantly higher fraction of its stellar population is made up of high-mass, high-energy stars. The violent conditions of its birth, the intense external pressure, the incredible turbulence, and the sheer density of the gas seem to have skewed the fragmentation process, making it easier for large, massive clumps to form and collapse. This isn't just a minor statistical fluctuation, it's a fundamental shift in the outcome of star formation, directly imprinted by the environment. The consequences of this shift ripple across the entire galaxy. A top-heavy initial mass function is a recipe for a short, spectacular, and transformative life. A population with more massive stars will produce far more ultraviolet radiation, flooding its surroundings with energetic light that can ionize gas and heat it, preventing further collapse. It will host many more core collapse supernovae at a much faster rate, injecting enormous amounts of kinetic energy and newly forged heavy elements into the interstellar medium in a very short period. The chemical signature of such a burst would be distinct, heavily weighted towards the alpha elements produced by massive stars, with less of the later iron peak contribution from slower evolving white dwarfs. The feedback from such a population is so intense that it can actually self-regulate, quickly blowing apart the very cloud that created it and shutting down star formation in that region almost as soon as it began. This means that the initial mass function is not just a passive memory, it is an active governor of a galaxy's growth and evolution. A top-heavy IMF in a starburst region can lead to a brief, brilliant flash of galactic activity that rapidly enriches its surroundings and then burns out, while a bottom-heavy IMF in a quiet region allows for slow, steady, and sustained star formation over billions of years. By studying the IMF in different clusters and different types of galaxies, astronomers are essentially reading the fine print on the contract of galactic evolution, understanding how the physical conditions at the moment of star birth set in motion a chain of events that will dictate the future light, chemistry, and structure of an entire galactic ecosystem for eons to come. Just as a spinning ice skater speeds up by pulling in their arms, a star's rotation carries a deep and dynamic memory of its earliest moments, a direct echo of the chaos or calm that reigned in the cloud of its birth. This spin rate isn't arbitrary, it's a fossilized record of the star's initial angular momentum, a property imprinted upon it by the specific physical conditions of its natal nursery. The key factor is turbulence. Imagine a vast, chaotic molecular cloud, rippling with internal supersonic motions and shock waves from nearby supernovae. As this turbulent cloud fragments into dense cores, each collapsing clump inherits a wild, chaotic spin from the violent motions around it. Stars born from such a turbulent environment will naturally be fast rotators, spinning rapidly from the very moment they ignite, their youth defined by a frantic, energetic whirl. Conversely, a star that forms in a serene, quiet, and cold region of a cloud, where the gas is settling down calmly, will begin its life with a much more sedate and leisurely rotation. Its slow spin is a permanent memory of a peaceful and orderly birth, but the story of a star's spin is not just about the initial kick, it's also a tale of magnetic braking, a fundamental process that governs a star's rotational life story. A newborn star is not an island. It is surrounded by a vast, spinning disk of gas and dust from which it continues to accrete material. This young star also generates a powerful magnetic field of its own. This field acts like an invisible tether connecting the star's surface to its outer disk. As the star rotates, its magnetic field sweeps through the disk, effectively acting as a powerful brake, transferring the star's angular momentum out into the disk and dramatically slowing its spin over time. The efficiency of this braking depends heavily on the star's mass and internal structure. This is why we see such a clear and beautiful pattern when we measure the rotation periods of stars in clusters of different ages. In a very young cluster like the 1-million-year-old Orion Nebula cluster, stars of all masses are found spinning at a wide, frantic range of rates, their rotation yet to be tamed. But in an older cluster like the 600-million-year-old Hyades, a clear relationship has emerged. The lower mass stars have been effectively braked and now rotate slowly, while the more massive stars, whose different internal structures make them less susceptible to magnetic braking, are still spinning rapidly. This allows astronomers to use rotation as a highly accurate clock for determining the ages of stars, a technique called gyrochronology. By simply measuring how fast a star is spinning, we can estimate its age with remarkable precision, adding a powerful dynamic dimension to our cosmic timelines. This rotation does more than just tell time. It actively shapes the star's chemical story through a process known as rotational mixing. A star like our Sun has a layered structure with a convective outer zone and a radiative interior. Elements forged by fusion in the core are typically trapped there, unable to reach the surface. But a star's spin can change all that. Rapid rotation creates powerful shear forces at the boundary between these layers, churning the stellar plasma and dredging up material from the deep interior to the observable surface. This can dramatically alter the chemical signature we see, creating stars with bizarre and puzzling atmospheres. The classic examples are the metallic line of stars, or stars. These are stars that should, based on their temperature and mass, have fairly normal atmospheres. Instead, spectroscopy reveals they have strange overabundances of certain heavy elements like iron and nickel, and surprising deficits of others like calcium and scandium. For a long time, this was a mystery. The solution lies in rotation, or rather, the lack of it. It's believed that these stars are actually the slowly rotating components in a binary system. Their more massive companion star might have transferred material to them, spinning them up, and then the magnetic braking from that companion somehow slowed them down to an unusually slow rotation. This peculiarly slow and stable rotation allows for a very quiet atmosphere where heavier elements, pushed by radiation pressure, can gently float to the top while lighter elements sink out of sight. Their peculiar chemistry is therefore not a memory of their birth cloud, but a later alteration caused by their specific rotational history and their companionship with another star. By mapping the rotation rates of thousands of stars across the Milky Way, from the ancient, slowly spinning denizens of the halo to the youthful, rapid spinners in the spiral arms, we are effectively writing a biography of angular momentum in our galaxy. We can trace how the average spin of newborn stars has changed over billions of years, which in turn tells us about the evolving levels of turbulence and magnetic field strength in giant molecular clouds throughout cosmic time. This dynamic memory provides a unique window into the physical conditions of star formation that complements the chemical story told by metallicity. A star's rotation is a living record of its youth, a persistent spin that connects it directly to the specific environment and intricate physics of the cloud that gave it life, a ghostly momentum that has been preserved for millions or even billions of years. Just as the spin of a star tells a tale of its youth, the star's magnetic personality, its fiery temper and stormy surface, holds another deep and dynamic memory. This isn't a quiet, steady glow. It's the record of a star's inner turmoil, a stormy disposition imprinted at birth and played out over its entire lifetime through starspots, flares, and powerful outbursts. This magnetic activity is the direct product of a star's internal dynamo, a colossal natural engine deep within its interior that generates its magnetic field. Unlike any engine, its power and character are determined by its fuel and its design. For a star, that fuel is the churning, convective motion of its plasma and the speed of its rotation. These two factors, both set during the star's formation, are the primary architects of its magnetic destiny. A star born with a rapid spin and a deeply convective interior will naturally generate a far more powerful and turbulent magnetic field than a slow, sedate star. This means a star's propensity for flares and spots isn't random. It's a direct and lasting memory of the specific rotational and structural blueprint it was assigned at birth. We can see this magnetic memory most vividly by looking at stellar families, particularly young open clusters. The Pleiades cluster, that beautiful bunch of blue stars visible in the night sky, is a perfect example. The stars here are cosmic teenagers, a mere 100 million years old. They are still spinning rapidly, their youthful energy undimmed by the magnetic braking that will eventually slow their older cousins. And they are absolutely bursting with magnetic activity. Observations across the electromagnetic spectrum, from X-rays to radio waves, reveal them to be incredibly flare-prone, with surfaces mottled by enormous starspots that are the stellar equivalent of raging sunspots, but on a far grander scale. Their coronas, their superheated outer atmospheres, are brilliantly intense, glowing with X-rays that betray a fierce level of magnetic heating. This hyperactive state is a direct signature of their youth and their formation environment. They remember the turbulent, crowded nursery they were born in, a place that gave them a fast spin and a consequently violent magnetic personality. As these stars age and their rotation gradually slows, their magnetic dynamo will weaken, and their flaring tantrums will become less frequent and less intense. The Sun, now a settled middle-aged star, has a well-behaved 11-year activity cycle, a far cry from the constant stellar storms of its youth. This life cycle of magnetic activity, from youthful frenzy to mature stability, is a clock that astronomers can use to gauge the age of a star simply by measuring how stormy its surface is. But a star's magnetic story can be rewritten by companionship. Just as a binary companion can alter a star's rotation and chemistry, it can also dramatically affect its magnetic activity. In a close binary system, the gravitational tug of war between the two stars can lock their rotations, forcing them to spin in sync with their orbital period. This process, called tidal locking, can prevent the natural spin down that occurs in single stars. The result is a star that maintains a rapid rotation, and thus a powerful, youthful dynamo billions of years after it should have calmed down. This can lead to a system where both stars are perpetual flare stars, bathing any orbiting planets in a relentless barrage of high-energy radiation and stellar winds. Conversely, the presence of a massive planetary system, like a hot Jupiter orbiting extremely close to its star, might also influence the host star's magnetic activity through tidal interactions, though this is a subtle effect that astronomers are still working to confirm. The key point is that a star's current level of activity is not always a pure memory of its birth. It can be a complex narrative shaped by its subsequent gravitational relationships. This stellar activity is far more than just a fascinating curiosity. It is the primary dictator of habitability for any planets that might orbit the star. A star's magnetic personality defines the very nature of the space weather in its system. For a planet orbiting a hyperactive young star or a tidally locked binary companion, the environment is one of constant peril. Frequent, powerful flares can strip away a planet's atmosphere over time, especially if that planet is a rocky world in the so-called habitable zone. These flares deliver deadly doses of ultraviolet and X-ray radiation that can sterilize a planet's surface and break down complex molecules necessary for life. The relentless stellar wind, accelerated by the strong magnetic field, creates a constant pressure that can erode a planetary magnetic shield and compress its protective magnetosphere. A planet needs a robust magnetic field of its own to deflect this onslaught, but even that might not be enough against the most violent stellar tantrums. Our own Sun, in its quieter middle age, provides a far more stable and nurturing environment, with its occasional storms offering a manageable level of space weather. The difference between a life-bearing world like Earth and a barren, irradiated rock could very well come down to the magnetic memory of its parent star, whether that star was born with or later acquired a calm and stable disposition. By surveying the magnetic activity of stars across the Milky Way, from the ancient, quiet stars in the halo to the frenetic young stars in the spiral arms, astronomers are piecing together the magnetic evolution of our entire galaxy. They can map how the average level of stellar storminess has changed over cosmic time, which in turn reflects the changing conditions in star-forming regions. Was the early galaxy, with its higher rates of star formation and closer stellar encounters, a place of more frequent and violent flares? Did that intense radiation environment in the galactic center influence the types of planets that could form there? The collective magnetic activity of all the stars in a galaxy contributes to its overall energy output in high-energy wavelengths, affecting the ionization state of its interstellar gas and potentially influencing the rate of star formation itself. The sunspot cycles and flare rates of countless stars are like individual notes in a grand galactic symphony, each one a memory of its own formation and history, but together telling the story of how magnetism, one of the universe's most fundamental forces, has shaped the lives of stars and the potential for life throughout the cosmos. But the story of stellar memory isn't just about which elements are made. It's a far more intricate tale of how much of each element a star produces over its lifetime, and how that specific recipe depends on the star's most fundamental properties. This concept is known as nucleosynthesis yield, and it represents one of the most precise and detailed memories a stellar generation can pass on. Think of it not as a simple list of ingredients, but as an exact, weighted recipe that changes dramatically depending on the size of the cosmic chef and the quality of the raw materials they started with. A massive star and a low-mass star, even if born from the same cloud at the same time, will leave behind completely different chemical legacies. Their yields, the total mass of each element they manufacture and eject back into space, are their final, lasting contributions to the galactic chemical pool, and these outputs are permanently recorded in the atmospheres of the stars that form next. The division of stellar labor is stark and fundamental. Massive stars, those titans born with more than 8 times the mass of our Sun, are the universe's primary foundries for the alpha elements. Their lives are a frantic race against time, burning through their nuclear fuel in just millions of years. In their incredibly hot and dense cores, they fuse elements all the way up to iron through a series of successive stages: hydrogen to helium, helium to carbon, carbon to neon, neon to oxygen, and oxygen to silicon, finally creating an iron core that spells their doom. When they inevitably explode as core collapse supernova, they blast this entire inventory of newly forged material into the cosmos. Their yield is overwhelmingly rich in oxygen, magnesium, silicon, and calcium. They are the primary source of these fundamental building blocks for rocks and planets, and they disperse them with tremendous violence and efficiency. In complete contrast, low-mass stars like our Sun are the universe's slow and patient artisans, specializing in a completely different set of elements. Their contribution comes not in a spectacular explosion, but in a gentle, prolonged exhale at the very end of their lives. After spending billions of years steadily burning hydrogen, a Sun-like star will eventually evolve into a red giant and then enter a final, complex phase known as the asymptotic giant branch, or AG. During this AGB phase, something remarkable happens deep within the star. Helium burning occurs in a shell around the core, and the conditions become perfect for the slow neutron capture process, or S process. In this process, atomic nuclei slowly absorb neutrons one at a time, gradually stepping up the periodic table to create heavier elements like strontium, barium, and lead. But the star's work isn't done yet. It also engages in something called dredge up, where deep convective currents bring these newly created heavy elements from the interior all the way up to the surface. Finally, in a last act of cosmic recycling, the star gently sheds its entire enriched outer envelope through a powerful stellar wind, creating a beautiful planetary nebula. The yield from a low-mass star is therefore heavily weighted towards carbon, nitrogen, and the suite of S-process elements. It's a quiet, generous gift of complexity, delivered not with a bang but with a whisper. When astronomers look at the chemical makeup of a galaxy, they are essentially looking at the integrated yield of countless generations of stars. The specific ratio of elements they find, the amount of oxygen compared to iron, or the abundance of carbon relative to barium, acts as a detailed historical ledger. It reveals the dominant mass of stars that contributed to that environment over time. For instance, a region with a very high ratio of oxygen to iron tells us that its chemical history was dominated by the rapid, early explosions of massive stars before the slower evolving low-mass stars had a chance to contribute their iron-rich yields from type Ia supernova. Furthermore, the overall amount of enrichment reveals the integrated initial mass function, whether star formation tended to produce lots of high-mass stars or was skewed towards low-mass ones. A galaxy that had a top-heavy initial mass function, producing a greater proportion of massive stars, would have a very different elemental signature today than a galaxy that primarily formed smaller, longer-lived stars. Some of the most fascinating and puzzling entries in this cosmic ledger are the carbon-enhanced metal-poor stars, often called SEMP stars. These are ancient, extremely metal-poor stars that should, by all rights, have very little carbon. Yet, their spectra show a surprising and dramatic overabundance of carbon, sometimes by factors of hundreds or even thousands compared to the iron content. This bizarre signature is a direct memory of a very peculiar nucleosynthesis yield from the very first generations of stars. It suggests that the first supernova in the universe didn't follow the standard rules. They might have been faint supernova, or ones that experienced extensive mixing and fallback, where the inner iron core fell back into a black hole, trapping the iron and preventing it from being ejected, while the outer carbon-rich layers were still blown out into space. The yield from these first stars was therefore completely anomalous, a cocktail rich in carbon but poor in iron. The SEMP stars that formed from this polluted gas carry this strange recipe as a permanent memory, a direct fingerprint of the unique and poorly understood physics that governed the deaths of the very first stars, offering a tantalizing window into the exotic nucleosynthesis that seeded the cosmos with its first heavy elements and set the stage for all the complex chemistry that was to follow. We have journeyed through the memories written in starlight and motion, but some of the universe's most detailed records are kept not by blazing suns, but by the tiniest, darkest particles drifting in the void. This is the memory of cosmic dust, the microscopic soot and sand that fills the spaces between the stars. To overlook this dust is to miss a fundamental chapter of the story, for these tiny grains are far more than simple obscuring smoke. They are the ultimate archivists, carrying within their crystalline structures a perfect atom-by-atom record of the specific stellar furnaces that forged them. Each minuscule speck is a time capsule, a piece of stellar DNA that gets woven into the fabric of every new star and planet, making dust one of the most powerful and tangible messengers of galactic history. The origin story of these grains is a tale of stellar life and death. They are not formed in the vast emptiness of space, but in the intense, complex environments of aging stars. In the extended, bloated atmospheres of cool, pulsating red giants and asymptotic giant branch stars, conditions become just right for condensation. Atoms of carbon, silicon, and other heavy elements bump into each other, and much like water vapor condensing on a cold window pane, they begin to stick together, forming tiny seed particles. These seeds then grow as more atoms deposit onto them, eventually becoming full-fledged dust grains that are then pushed out into the galaxy by the star's powerful stellar wind. This is a gentle, continuous form of recycling, but dust is also born from the most violent events in the cosmos. The colossal shock waves of supernova explosions provide another potent crucible. The expanding ejecta, rich with newly synthesized elements and rapidly cooling, creates a fertile ground for the rapid condensation of dust, producing a different family of grains with a distinct chemical signature. The type of star that dies dictates the type of dust it produces. An oxygen-rich star will forge grains of silicates, essentially tiny particles of rock and glass, like minuscule sand grains. A carbon-rich star, however, will manufacture grains of graphite and even more complex carbon compounds, the sooty remains of its nuclear burning. This is why the composition and abundance of dust act as a direct barometer for a galaxy's evolutionary state. A galaxy in the throes of a starburst phase, like the famous M82, is a dust factory operating at a frantic pace. Its interstellar medium is flooded with fresh grains from the constant deaths of its short-lived, massive stars. This dust is typically rich in silicates and carbonaceous materials, and it is abundant, often obscuring the brilliant core of the galaxy from our view in optical light, though it glows brilliantly in the infrared. Conversely, an old, quiescent elliptical galaxy, whose star formation ceased billions of years ago, has a very different dust profile. Its interstellar medium has long since been depleted or heated beyond the point of dust formation, and any remaining grains are likely ancient relics or material accreted from cannibalized dwarf galaxies. The dust content of a galaxy is therefore a living memory of its recent star formation activity, a measure of how many massive stars have lived and died in a given period. polluting the environment with their solid, microscopic ashes. The most astonishing proof of this stellar ancestry comes from presolar grains, tiny mineral crystals found right here on Earth, embedded within primitive meteorites. These are not samples of the early solar system. They are literal stardust, solid pieces of other stars that predate the formation of our Sun. Through meticulous laboratory analysis, scientists can isolate these grains, which include diamonds, graphite, silicon carbide, and corundum, and analyze their isotopic compositions. And here's the miracle: the isotopic ratios within each grain are wildly anomalous compared to the average mix found in our solar system. They are completely unique. A grain with a highly unusual ratio of carbon-12 to carbon-13 might be identified as a relic from a red giant star. Another grain, rich in specific isotopes of calcium and titanium, can only have formed in the ejecta of a type Roman II supernova. Some even carry the signature of the slow neutron capture process, pinpointing their origin to the winds of an AGB star. Holding a meteorite containing these grains is like holding a collection of fossils from different, long-dead stellar species. They are the only tangible samples we have of specific stellar nucleosynthesis events, providing ground truth data that allows us to test and refine our models of how elements are forged in stars. They are the ultimate physical evidence, connecting the abstract concept of nucleosynthesis directly to our hands. Beyond being mere messengers, dust plays an absolutely critical and active role in the galactic ecosystem. It is the essential midwife for the birth of new stars. Its most important function is cooling. A giant molecular cloud of pure hydrogen and helium gas is very inefficient at losing the heat generated by gravitational collapse. As the cloud contracts, it heats up, and the increased internal pressure fights back against gravity, putting a brake on the star formation process. Dust grains solve this problem. They are incredibly efficient at absorbing the heat energy from the gas and then radiating it away as infrared light. This acts as a cosmic radiator, allowing the cloud to cool down dramatically. As the cloud cools, its internal pressure drops, allowing gravity to win and the cloud to fragment into ever denser cores that can eventually collapse to form stars. Without this dust-driven cooling, star formation would be a much slower and far less efficient process, and galaxies might look very different. Furthermore, dust grains provide a protective shield. The fragile molecules that are the first steps toward complex chemistry, most importantly molecular hydrogen, are easily broken apart by the harsh ultraviolet radiation from nearby stars. Dust grains offer them a safe haven. Molecules can form on the solid surfaces of these grains, protected from the destructive radiation. The dust-shielded cores of molecular clouds are thus the only places in the universe where the complex chemistry necessary for planet formation and ultimately life can begin. The presence of dust doesn't just allow stars to form. It allows for the rich, complex planetary systems that orbit them to emerge from the darkness. Yet even the precise chemical ledgers written in elemental abundances only tell part of the story. To uncover the most intimate details of a star's origin, we must drill down to an even finer level of detail, to the very heart of the atom itself. This is the realm of isotopic ratios, where the specific varieties of an element, each with a different number of neutrons in its nucleus, act as exquisitely sensitive cosmic clocks and thermometers. While a star's overall ion content might tell us it formed from gas enriched by supernova, the precise ratio of one ion isotope to another can reveal the exact temperature inside that supernova's core during the moment of its explosive death, or pinpoint exactly how long ago that event occurred. These subtle nuclear fingerprints are the most precise memories a star can carry, offering a level of detail that transforms our understanding from a broad historical narrative into a finely resolved, moment-by-moment account of cosmic history. The power of these isotopic clocks lies in the fact that many isotopes are radioactive, decaying into a stable daughter product at a rate so predictable it is one of the fundamental constants of the universe. The most famous of these cosmic chronometers is the decay of uranium-238 into lead-206. With a half-life of about 4.5 billion years, this timescale is perfectly suited for measuring the ages of the oldest stars and the events that enriched them. By carefully measuring the minuscule amounts of these isotopes in a star's atmosphere, a feat of extraordinary spectroscopic precision, astronomers can calculate how long that radioactive material has been decaying. This is how we can date the formation of our own solar system by looking at the Sun. Its isotopic ratios, particularly for elements like uranium and thorium, reflect the average composition of the galactic neighborhood 4.6 billion years ago, acting as a frozen snapshot of the interstellar medium at that specific moment in the Milky Way's history. It's a precise timestamp telling us not just that the Sun is old, but exactly when it was born relative to the grand timeline of galactic evolution. But these ratios are more than just clocks. They are also incredibly sensitive thermometers and pressure gauges that remember the specific conditions inside the stellar furnaces that forged them. Different nuclear processes favor the creation of specific isotopes depending on the temperature and density of the environment. A key example is the ratio of carbon-12 to carbon-13. This ratio is highly sensitive to the temperature at which nuclear fusion occurs. In the core of a Sun-like star, where hydrogen burns at a relatively steady rate, a certain balance between these two carbon isotopes is achieved. However, in the more complex, layered burning shells of a massive star barreling towards supernova, or in the helium-burning core of an aging giant, the temperatures can be vastly higher, producing a completely different carbon isotope ratio. When that star dies and scatters its ashes, that specific ratio is imprinted on the surrounding gas. Therefore, when we measure an anomalous carbon ratio in a newly formed star, we are not just measuring carbon, we are taking the temperature of the interior of a long-dead star that died billions of years before. We are reading a memory of the precise thermal conditions of a specific nucleosynthesis event that occurred in the distant past. Some of the most baffling and exciting stellar memories are found in stars that display isotopic ratios that defy all known models of nuclear physics. The most extreme example is Przybylski's star, a peculiar object that has left astronomers scratching their heads for decades. Its spectrum is a bizarre menagerie of spectral lines indicating highly unusual abundances of strange elements like strontium, holmium, and even short-lived radioactive elements like promethium, which has a half-life of only a few years. The presence of such ephemeral elements suggests they must be continuously created within the star itself, as they would have decayed away eons ago otherwise. The isotopic ratios in Przybylski's star are so anomalous that they point to nuclear processes we do not yet understand, possibly involving unknown states of matter or even the existence of stable superheavy elements that have not yet been discovered on Earth. This star's atmosphere is a message in a bottle, carrying a memory of physics that may operate under conditions so extreme we cannot yet replicate them in any laboratory, offering a tantalizing glimpse into the fundamental laws that govern the hearts of stars. While measuring these delicate isotopic signatures in the light of distant stars is a monumental technical challenge, we have another, even more direct way to study them. We can hold them in our hands. Presolar grains, those microscopic pieces of stardust found in primitive meteorites, are the ultimate physical archives of isotopic memory. Unlike a stellar spectrum, which gives us a blended average of an entire star's atmosphere. Each individual presolar grain comes from a single stellar source. In the laboratory, we can place a single grain under a mass spectrometer and measure its isotopic composition with incredible accuracy. The results are stunning. One silicon carbide grain might have a silicon isotope ratio that screams, "I was born in the wind of a carbon-rich AGB star." Another, a tiny nanodiamond, might have a xenon isotope signature that could only have been produced in the violent crucible of a supernova explosion. These grains are not just souvenirs, they are frozen, microscopic pieces of data, each one a pristine and unaltered memory of the specific nuclear process and the specific star that created it. They allow us to take apart the blended soup of the solar system's composition and identify the individual stellar chefs who contributed to the recipe, providing a granularity to cosmic archaeology that light alone can never achieve. This isotopic memory, whether read from the faint light of a distant sun or measured in a microscopic speck of dust, provides the finest grain tool we have for reconstructing the history of our galaxy, turning the abstract concept of nucleosynthesis into a precise and quantifiable science. It's as if every star in the sky is a grand cosmic bell, ringing with a complex symphony of internal vibrations. These aren't random shudders, they are precise, resonant frequencies that pulse deep within a star's heart, and they hold the most intimate secrets of its internal architecture. This field of study, known as asteroseismology, allows us to become cosmic listeners, tuning into the natural music of the spheres to decipher the hidden structure and history written in a star's oscillations. Just as geologists use seismic waves from earthquakes to map Earth's interior, astronomers use the tiny, rhythmic dimming and brightening of a star's light to see deep inside it, uncovering details about its density, temperature, composition, and even how it spins deep within its hidden layers. This vibrational memory is perhaps the most direct window we have into the present-day state of a star, a state that is the direct and inevitable result of its entire life story, from its birth in a specific cloud to its eventual fate. The key to unlocking this stellar music lies in understanding that a star is not a silent, solid ball. It is a vast, churning sphere of superheated plasma, and it naturally pulsates in many different modes simultaneously. Think of it like a musical instrument. A drum skin can vibrate in a fundamental tone, but also in a series of overtones. A star does the same thing. Different pulsation modes or oscillations probe different depths within the star. Some modes are like deep, resonant gongs that travel right through the star's core, while others are like higher-pitched ripples that only skim the surface. By meticulously measuring the frequencies of all these different modes, essentially identifying all the notes in the star's chord, astronomers can perform a stellar ultrasound. They can build a detailed, layer-by-layer model of the star's internal structure. The frequencies tell us about the density and pressure at every depth. A higher frequency in a certain range might indicate a denser, more compressed region, while a lower frequency suggests a more diffuse, gaseous zone. The way these frequencies change over time can even reveal the star's internal rotation, showing how the core might spin at a different rate than the surface, a phenomenon that holds crucial clues about how angular momentum is transferred within a star over its billions-year lifespan. The revolution in this field was supercharged by space telescopes like NASA's Kepler mission. Kepler's primary job was to find planets by staring unblinkingly at a single patch of sky for years, measuring the incredibly tiny dips in starlight caused by a planet passing in front of its star. But this same exquisite precision, this ability to detect changes in brightness of just 1 part in a million, made it the perfect instrument for asteroseismology. It could detect the faint, rhythmic pulsing of tens of thousands of stars simultaneously. The data it returned was a gold mine. For many stars, especially those similar to our Sun, astronomers were able to measure their oscillation frequencies with such accuracy that they could determine the star's age with a precision of just a few percent. It's a far more direct clock than methods that rely on surface properties alone. This is because the pulsation frequencies are exquisitely sensitive to the star's internal sound speed, which in turn depends on its internal composition, specifically how much hydrogen it has left to burn in its core. A younger star has a full core of hydrogen, while an older star has a core filling up with inert helium. This change in composition alters the internal conditions and thus the star's natural resonant frequencies. By listening to the star's song, we can hear its age, but the insights go far beyond just a birthday. Asteroseismology has allowed us to probe complex physical processes that were previously only theoretical. A great example is something called convective overshoot. Our models of stars include large convection zones where bubbles of hot plasma rise, cool, and sink, much like water boiling in a pot. The boundaries of these zones are critical for understanding how stars mix their fuel. Theory suggested that these convective bubbles wouldn't stop neatly at a defined border. They would have momentum and overshoot a short distance into the stable region. Proving this was difficult until asteroseismology. By analyzing the precise oscillation patterns of certain stars, astronomers found evidence that the chemical composition changed more gradually at the edge of the convection zone than standard models predicted. This was the smoking gun for overshoot. The star's vibrations remembered the physical process of those bubbles plunging just a little deeper, subtly altering the internal structure in a way that only this precise technique could detect. This allows us to refine our fundamental models of how stars work, making them more accurate and predictive. The power of this technique multiplies when we apply it to stars that are part of a cluster. As we've discussed, all stars in a cluster are born at the same time from the same cloud, so they share a common age and initial chemical composition. However, they have different masses. This makes a star cluster a perfect natural laboratory for studying stellar evolution. By performing asteroseismology on dozens or even hundreds of stars within a single cluster, a practice called ensemble asteroseismology, we can see how the internal structure and evolutionary state change perfectly and predictably with mass. We can see the precise point on the Hertzsprung-Russell diagram where stars of a certain mass begin to exhaust the hydrogen in their cores and start their journey toward becoming red giants. This vibrational census of an entire stellar family allows us to measure the tiny age spread within the cluster itself. Did all these stars form in a single, rapid burst, or was there a prolonged period of birth? And then use that cluster as a calibrated benchmark for understanding the ages of isolated stars throughout the galaxy. The collective hum of a star cluster is a detailed history of its formation, a vibrational memory that ties together the lives of hundreds of stars into a single, coherent story of their shared origin, providing a robust framework for understanding the timeline of star formation and evolution across the entire Milky Way. Yet for all the intricate stories written in a star's spin and magnetic field, there is an even more dramatic way a star's memory can be rewritten, not by its own internal processes, but through the intimate gravitational embrace of a companion. We now venture into the complex world of binary star systems, where two stars are locked in a cosmic dance that can last for billions of years. This partnership creates a powerful and often chaotic recorder of events because the lives of these stars become deeply intertwined in a way that can completely overwrite their original histories. Material can flow between them, their structures can be violently merged, and one star's dramatic evolution can directly and permanently alter the very composition of its partner. This makes binary systems far more than just double points of light. They are dynamic laboratories where we can observe processes of cosmic recycling and stellar metamorphosis that are impossible for a single, isolated star to ever experience. Perhaps the most direct way a binary system preserves and alters a memory is through the literal transfer of matter from one star to the other. This process, called mass transfer, can leave an indelible chemical mark on the receiving star, a kind of cosmic tattoo that tells a story of stellar evolution and sacrifice. A perfect example of this are the so-called barium stars. These are typically older, red giant stars that show a puzzling and significant overabundance of elements like barium, strontium, and other rare earth metals. For a long time, this was a profound mystery. These specific elements are created by the slow neutron capture process, or S process, which occurs deep in the interiors of aging, asymptotic giant branch stars. But a single, isolated red giant wouldn't be able to bring these newly forged elements to its surface in such vast quantities. The solution to the mystery requires a partner. Astronomers now understand that a barium star was not always alone. It once had a companion, a slightly more massive star that raced through its life cycle faster. That companion lived, died, and left behind a tiny, dense white dwarf remnant. But in its final, dramatic throes as an AGB star, it became bloated and began to shed its enriched outer layers into space. The barium star, its binary companion, was right there to gravitationally capture a significant portion of this stellar wind, which was heavily laden with the S-process elements freshly minted in the companion's interior. The receiving star's atmosphere was thus polluted, its chemical passport stamped not just by the cloud it was born from, but by the death throes of its closest neighbor. Today, we can often still detect the faint white dwarf companion, silently orbiting the enriched giant, serving as the silent witness to this ancient act of cosmic recycling that occurred billions of years ago. An even more extreme example of binary interactions rewriting a star's history is the phenomenon of blue stragglers. Imagine looking at a beautiful, ancient globular cluster where all the stars formed at the same time over 10 billion years ago. According to our understanding of stellar evolution, all the massive, bright blue stars should have burned out and died eons ago. The only stars left should be the older, redder, lower mass ones. Yet, in the hearts of these clusters, astronomers often find a few stars that break all the rules, stars that are hot, blue, and massive, shining brilliantly as if they were youthful, surrounded by a population of ancient red stars. These are the blue stragglers, and they are stellar anomalies that simply shouldn't exist in such an old environment. The most widely accepted explanation for their rejuvenated appearance is once again binary interactions. One scenario is that two lower mass stars, through a complex gravitational dance, actually collide and merge into a single, more massive star. This new, combined star has a fresh supply of hydrogen fuel and a higher mass, making it appear hotter, bluer, and younger than its peers, a stellar phoenix born from a merger. Another possibility is that one star in a binary system accretes so much mass from its companion that it is effectively rebooted, gaining mass and luminosity and extending its life on the main sequence. In both cases, the blue straggler's apparent youth is a complete illusion, a memory not of a recent birth but of a violent gravitational encounter that fundamentally altered its structure and reset its evolutionary clock. These dramatic interactions, mass transfer, mergers, and the violent common envelope, phases where one star expands to engulf its companion, complicate the work of a galactic archaeologist immensely. A star with a bizarre chemical signature might not be a pristine relic from the early universe. It might simply be the beneficiary of a cosmic blood transfusion from a nearby companion. A star that looks suspiciously young in an old cluster might not be an error in our theories, but a product of stellar cannibalism. Disentangling these effects is a monumental task. However, this complexity is also a gift. By studying the populations of these chemically peculiar stars and blue stragglers in different environments, we gain invaluable information about the rate and nature of binary evolution throughout the galaxy. Are binary interactions more common in the dense, crowded centers of globular clusters where close encounters are frequent, or do they occur at a steady rate everywhere? The answers to these questions help us build a more complete picture of stellar dynamics and life cycles. This dynamic memory shows us that stars are not always the solitary, stoic historians we often imagine them to be. They can be partners, predators, and even parasites, capable of stealing mass, altering compositions, and creating entirely new stellar identities through their gravitational relationships. Their stories are not always solitary, they are often duets and sometimes a complete rewrite of the original score. But the pristine chemical record of a star's birth is not always perfectly preserved. Sometimes it can be contaminated, even overwritten, by events that happen billions of years later. Imagine a star that has lived a quiet, peaceful life, its atmosphere a perfect time capsule of its birth cloud. Then, late in its existence, it ventures through a dense cloud of interstellar pollution or has a close encounter with a companion, and its surface is suddenly painted with elements that are not its own. This process, known as external accretion, is a form of cosmic contamination that can obscure a star's original memory, presenting a formidable challenge to astronomers trying to read its history, but also opening a surprising window into other, equally fascinating cosmic processes. Some of the most compelling evidence for this late-stage pollution comes not from living, fusion-powered stars, but from the glowing embers of dead ones, white dwarfs. These are the Earth-sized cores left behind after Sun-like stars shed their outer layers, and by all rights, their surfaces should be pristine. The intense gravity of a white dwarf is so strong that any elements heavier than hydrogen or helium should sink almost instantly out of sight into its interior, leaving behind a pure atmosphere of the lightest elements. Yet, a significant fraction of these dead stars show something astonishing. Their spectra reveal clear, undeniable lines of heavy elements like silicon, iron, magnesium, and even calcium. This is the cosmic equivalent of finding fresh soot on a perfectly clean white sheet. The only possible explanation is that these white dwarfs are actively accreting rocky material from their surroundings. They are, in essence, consuming the shattered remains of their own planetary systems. This isn't just a theoretical idea, it's a direct observation. The pattern of elements seen in the atmosphere of a polluted white dwarf often matches the composition we would expect from the crust and mantle of a rocky planet like Earth. By carefully analyzing this pollution, astronomers can perform a kind of remote planetary autopsy, determining the bulk composition of exoplanets that we could never hope to see directly. A white dwarf with too much iron might be gorging on a planetary core. One rich in olivine might be feasting on mantle material. This grisly act of cosmic cannibalism provides our clearest window into the building blocks of planets around other stars, all because a dead star's atmosphere was contaminated by the debris of its own children. The journey of a star can also lead it to sweep up material from the galaxy at large, further complicating its chemical story. Consider the enigmatic hypervelocity stars. These are stellar outcasts flung from the frenzied environment of the galactic center at speeds so great they are on a one-way trip out of the Milky Way entirely. As these lonely travelers race through the galaxy, they are not moving through a perfect vacuum. They plow through the thin, diffuse clouds of the interstellar medium. While the density is low over millions of years of travel, a hypervelocity star can potentially accrete a measurable amount of this external gas and dust onto its surface. This accreted material would have a chemical signature completely foreign to the star's original composition, reflecting the environment of the galactic halo or the distant regions between spiral arms through which it has traveled. For an astronomer trying to understand the star's origin, this presents a puzzle. Is its unusual surface chemistry a memory of a strange birthplace near the supermassive black hole? Or is it simply interstellar grime accumulated during its long, lonely exile? Disentangling that history is crucial for using these stars as probes of the galaxy's gravitational field. This process of late-life contamination creates a significant challenge for the field of galactic archaeology. A very old, metal-poor star in the halo should be a pristine relic of the early universe. But if that star has, during its long life, accreted even a small amount of metal-rich gas from a passing cloud, its surface will be artificially enriched. It could masquerade as a much younger star, leading us to misplace it on the galactic timeline. Conversely, a star could accrete material that is even more primitive than itself, though this is far less likely. The task, then, is to find ways to see through this contamination. One method is to look at elements that diffuse through the star's atmosphere at different rates, creating a chemical stratification that can betray the recent addition of external material. Another is to study binary stars. If both stars show the same chemical anomaly, it's likely a true birth signature. But if only one shows it, the fingerprint of accretion is clear. Learning to read past this cosmic contamination is essential for cleaning the lens through which we view the deep past, ensuring that the memories we decode are truly from the cradle and not just dust gathered on the journey. Yet even after a star has settled into its long, stable life, its journey is not entirely its own to dictate, for it is constantly subject to the subtle but persistent gravitational pull of the entire galaxy around it. This is the pervasive influence of galactic tides, a force that can act as a silent sculptor, gently shepherding stellar orbits or, in the most extreme environments, becoming a brutal executioner that can tear a star apart or dramatically hasten its demise. While we often picture stars leading isolated lives, they are in fact deeply embedded in the gravitational fabric of their galaxy. And this constant tidal interaction is a powerful environmental memory, a record of how a star's location and neighborhood have directly shaped its evolution and ultimate fate. The strength of these tidal forces is not uniform. It varies dramatically depending on where a star calls home. The most serene galactic habitats are the quiet, sparse outskirts of the galactic halo. Here, the gravitational pull from the collective mass of the galaxy is weak and steady, a gentle background hum that merely guides a star along its wide, lazy orbit over billions of years, leaving its internal life and structure almost entirely unaffected. It's a peaceful existence, but venture into the dense, bustling urban core of a galaxy, and the story changes completely. In these crowded central regions, a star is subjected to a relentless and complex gravitational field. It feels the combined pull from thousands of neighboring stars, the immense central bulge of the galaxy, and most powerfully, the supermassive black hole that typically lurks at the very center. This isn't a gentle guidance, it's a chaotic, stressful environment where a star's path can be violently perturbed, its structure stretched, and its lifespan potentially cut short. Nowhere is this tidal violence more extreme than in the immediate vicinity of a supermassive black hole. The gravitational gradient here is so unimaginably steep that the difference in pull between the side of a star facing the black hole and the side facing away can be millions of times stronger than anything the star experiences from its own gravity holding itself together. If a star ventures too close on a rogue orbit, it can be subjected to a process with the vividly descriptive name of spaghettification. The black hole's gravity will stretch the star vertically and compress it horizontally, pulling it into a long, thin strand of plasma before ultimately shredding it completely in a tidal disruption event. This is not a slow process. It can happen in a matter of hours. The stellar material is then drawn into an accretion disk around the black hole, heating to incredible temperatures and glowing brilliantly across the electromagnetic spectrum before vanishing past the event horizon. This catastrophic end is the ultimate example of a star's fate being dictated by its environment. Its death is not due to internal fuel exhaustion, but is a direct result of its location within the galactic gravitational landscape. The flash of light from such an event is a temporary but powerful memorial, a beacon that signals the violent tidal execution of a star by the most destructive force in the galaxy. But tidal forces don't just destroy, they can also fundamentally alter a star's life path in more subtle ways that can deceive an observer. In the dense cores of globular clusters, where stars are packed together 1,000 times more tightly than in our solar neighborhood, close gravitational encounters are not rare, they are a regular occurrence. When two stars pass near each other, their mutual tidal pull can literally strip away their outer layers. For a star that was evolving into a red giant, this tidal stripping can prematurely remove its hydrogen envelope, exposing its hotter, helium-burning core and making it appear, for a time, much younger and bluer than it actually is. This process can create objects that look like they should not exist in an ancient cluster, potentially blurring our interpretation of the cluster's age if we weren't aware of this environmental effect. Furthermore, these tidal interactions can fling stars out of the cluster entirely, creating hypervelocity stars that race across the galaxy, their very existence and high speed a permanent memory of the violent tidal forces that ejected them from their birthplace. For astronomers, accurately modeling these complex tidal interactions is not just an academic exercise, it is absolutely essential for building a true picture of a galaxy's history. The observed properties of a stellar population, its distribution of colors, brightnesses, and types of stars, are a direct reflection of both internal evolution and external environmental influence. If we see a lack of red giant stars in the very center of a cluster, it might be because tidal stripping has removed them, not because the cluster is young. If we see a surprising number of strange blue objects, they might be the tidally heated remnants of stellar collisions. By creating sophisticated computer simulations that account for the collective gravitational pull of every star, gas cloud, and dark matter particle, we can rewind the clock and understand how tides have sculpted a population over billions of years. This allows us to correct for these environmental effects and see past them to the true underlying age and history of the stars. The tidal forces a star experiences are thus a crucial, often overlooked part of its biography, a silent environmental pressure that reminds us that no star is an island. Its life story is inextricably linked to the gravitational tides of its galactic home, from the gentle currents of the halo to the crushing rapids at the heart of a black hole. But to truly grasp the profound secrets still locked within starlight, we must look to the future, to a new generation of cosmic observatories and analytical tools that promise to revolutionize stellar archaeology. The next decade will be a golden age, not just for seeing farther into the cosmos, but for seeing deeper into the very soul of a star, dissecting its light with a precision we can now only dream of. This isn't merely an incremental improvement. It's a quantum leap, a fundamental shift in our ability to interrogate the past and decode the faintest whispers of galactic memory carried across billions of years. Leading this charge are the titans of a new astronomical era, instruments of almost unimaginable power. The James Webb Space Telescope, already dazzling us with its infrared eyes, is just the beginning. Its true power for stellar archaeology lies in its ability to peer through the veils of dust that obscure the earliest epochs of star formation, and to analyze the atmospheres of the first stars in distant, infant galaxies. But it is the upcoming ground-based behemoths, the extremely large telescopes, that will truly shatter the limits of our vision. Imagine the European Southern Observatory's ILT, with a primary mirror stretching an incredible 39 meters across, a colossal eye that will gather more light than all of the historic great telescopes combined. This immense light-gathering power is the key. It allows us to not just see faint stars, but to break their light apart into exquisitely detailed spectra with a resolution far beyond anything possible today. We will move from reading the bold headlines of a star's composition to perusing the fine print detecting isotopes, measuring vanishingly rare elements, and uncovering subtle chemical signatures that are currently lost in the noise. For the first time, we will perform a detailed chemical census on stars in galaxies millions of light years away, comparing their enrichment histories to our own Milky Way to understand if our galactic story is typical or unique. This revolution in spectroscopy will be perfectly complemented by a simultaneous leap in astrometry, the precise measurement of stellar motions. The Gaia mission has already provided a stunningly detailed three-dimensional map of our galactic neighborhood, but the next generation of space-based astrometry missions will push this precision to another level entirely. They will measure the tiny wobbles in a star's position caused by the gravitational tug of orbiting Earth-sized planets and trace the subtle gravitational perturbations from dark matter subhalos with exquisite detail. By combining this ultra-precise kinematic data with the deep chemical profiles from the giant telescopes, we will be able to do more than just identify immigrant stars. We will be able to trace their paths back to their precise birthplace, identifying not just that a star came from a dwarf galaxy, but exactly which stream and which specific event brought it here, effectively writing a full biography for millions of individual stars. Yet, the sheer volume and complexity of data from these new instruments would be overwhelming, even paralyzing, without a parallel revolution in how we analyze it. This is where machine learning and artificial intelligence become the indispensable partners of the astronomer. These are not just tools for sorting data, they are new engines of discovery. Sophisticated algorithms will be trained on millions of simulated stellar spectra, learning to recognize the subtle patterns that correspond to specific formation scenarios. The chemical fingerprint of a neutron star merger versus a certain type of supernova, or the kinematic signature of a specific galactic merger event. They will sift through petabytes of data to find the rarest of needles in the cosmic haystack, perhaps identifying a single, crucial star with a unique isotopic ratio that overturns our current models of nucleosynthesis. This powerful synergy between human intuition and machine precision will allow us to move from studying individual stellar memories to understanding the entire galactic ecosystem as a complex, interconnected network of cause and effect. So what are the holy grails, the specific cosmic secrets these powerful new tools are designed to uncover? The ultimate prize remains the direct detection of a population 3-star, one of the mythical first generation of giants made only of hydrogen and helium. While their short lives mean we will likely never see one directly, their supernova left behind a very distinct chemical pattern in the next generation of stars. The next-generation telescopes will search for the most extreme metal-poor stars, those with not just low iron, but peculiar abundances of carbon, oxygen, and other elements that act as the unique fingerprint of a pair instability supernova, a titanic explosion from a star over 150 times the mass of our Sun that completely obliterates itself, leaving no black hole behind. Finding this signature would be like discovering the fossilized bone of a specific, long-extinct dinosaur, confirming a key prediction about the earliest moments of cosmic structure. Furthermore, we will be able to directly observe planet formation in a staggering variety of galactic environments, from the violent, metal-rich centers of starburst galaxies to the quiet, metal-poor outskirts of dwarf galaxies. This will finally allow us to answer the fundamental question of how a galaxy's large-scale properties, its chemistry and dynamics, directly determine the types of planetary systems it can build, bringing us closer than ever to understanding the galactic recipe for habitable worlds. This incredible future of discovery, where each point of light becomes an open book waiting to be read, fills astronomers with a palpable sense of excitement, a certainty that the next chapter in our understanding of the cosmos will be the most revealing yet. And so, as we decode these stellar memories, these whispers from across the abyss of space and time, we arrive at a realization that transcends the scientific and touches something profoundly, deeply human. This isn't just astrophysics, it is the greatest story ever told, and it is our story. Every single atom that makes up our bodies, our planet, and everything we have ever known or loved was forged in the heart of a star that lived and died long before our Sun was even a glimmer in a galactic cloud. The iron that carries oxygen in your blood was born in the cataclysm of a supernova. The calcium in your bones was a gift from the gentle exhale of a dying red giant. The very air you breathe is a legacy, a cosmic inheritance from generations of stellar lives that ended so that ours could begin. We are not just observers of the universe, we are a part of it, literally and physically. We are the universe become conscious, a way for the cosmos to look back upon itself and contemplate its own origins and its own majesty. This connection obliterates the illusion of separation, weaving us into the grand, intricate tapestry of cosmic evolution, from the first flash of the Big Bang to the complex thoughts swirling in your mind right now. It is a humbling and awe-inspiring unity. This perspective inevitably pushes our minds toward one of the most profound questions we can ask. If the universe follows the same physical laws everywhere, and if the same processes of star formation, planet building, and chemical enrichment are happening in 100 billion other galaxies, then are we truly alone? The study of stellar memories gives us a new way to approach this ancient mystery. If another civilization on a world orbiting a distant sun has also learned to read the light of their stars, they would be reading the very same story. They would see the same elemental patterns, the same supernova signatures, the same evidence of neutron star mergers. They would know, just as we do, that they are made of stardust. This shared cosmic narrative, written in the universal language of physics and chemistry, could be the closest thing we have to a common ground with intelligence we cannot yet imagine. It suggests that any technological civilization, no matter how alien its biology or culture, would have to grapple with the same fundamental truths about its origin. They would look up at their night sky and see not just points of light, but their own extended family tree, a genealogy written in fusion and fission. This doesn't prove they are out there, but it builds a powerful, logical framework for cosmic companionship, suggesting that the journey from stardust to sentience might be a path the universe travels not just once, but many times over. This leads us directly to a second, even more fundamental question about the nature of reality itself. As we use stellar memories to reconstruct the history of our galaxy, we are making a colossal assumption. that the laws of physics are constant and unchanging across billions of years and billions of light years. But what if they aren't? What if the fine structure constant which governs the strength of electromagnetic interactions was slightly different in the early universe? A tiny variation in this fundamental force would alter the energy levels within atoms, which would change the precise spectral lines we see in the light from the most ancient stars. The fact that we can identify the same elements in a 13-billion-year-old halo star as we can in our Sun, with spectral lines appearing exactly where our current physics says they should, is a powerful testament to the stability of the cosmos. It suggests that the rules of the game have not changed since the very beginning. Stellar memories thus become our ultimate laboratory for testing the constancy of nature's laws over timescales no earthbound experiment could ever hope to achieve. Every ancient star we analyze is a check on the reliability of reality itself, and so far, reality has proven to be remarkably consistent and trustworthy, a foundation upon which we can build our understanding of everything. Ultimately, the quest to understand what stars remember does more than just advance science. It nourishes the human spirit. It places our brief, flickering existence within a context of almost unimaginable grandeur and scale. It connects us to a past of titanic explosions and gentle stellar winds, and to a future that will unfold long after our civilization is dust. This knowledge is a form of time travel, a way to reach across the eons and touch the events that made our existence possible. It enriches our culture, our philosophy, and our art, providing a wellspring of wonder and a profound sense of perspective. In a world often consumed by petty divisions and short-term conflicts, the cosmic perspective reminds us of our shared origin and our common destiny on this pale blue dot. It teaches us humility, not by making us feel small, but by showing us that we are braided into the vast, beautiful, and ongoing story of the cosmos. We are the universe's way of understanding its own history, and in listening to the memories of the stars, we are finally coming home to our true place in the grand scheme of things, a place of connection, wonder, and boundless curiosity. From the pure, pristine hydrogen forged in the first moments of the Big Bang to the intricate gold filigree of a cherished necklace, we have journeyed through the deepest memories the cosmos has to offer. We have learned to listen as stars whisper their ancient secrets, revealing how the very fabric of a galaxy, its violent mergers, its quiet evolutions, its hidden dark matter skeleton is permanently encoded in their light, their motion, and their elemental soul. These are not just cold, scientific data points. They are the individual chapters of a grand, epic narrative, a story of construction and destruction on a scale so vast it defies human imagination. This narrative shows us that a galaxy is not a static painting but a living, breathing, and ever-changing entity, a great celestial organism that grows, consumes, and transforms over billions of years. And within that epic, we have found our own tiny, yet infinitely precious place. The iron in our blood, the calcium in our bones, the oxygen in our lungs, every atom that defines our physical existence was once part of a star that lived and died in the galactic disk long before our sun was born. We are not merely inhabitants of the universe, we are its product, literally stardust that has coalesced, become conscious, and now looks back up at the sky in wonder, seeking to understand its own origin. This profound connection is the most powerful takeaway from our journey. It dissolves the illusion of separation, weaving us directly into the cosmic story. We are the universe experiencing itself, a fleeting but sentient moment in a 13.8 billion-year continuum. The adventure of decoding these stellar memories is far from over. In fact, it is accelerating at a breathtaking pace. The next generation of telescopes, both on the ground and in space, will act as ever more sensitive cosmic hearing aids, allowing us to detect the faintest whispers from the most ancient stars. Advanced algorithms and machine learning will help us untangle the complex stories woven together in a single spectrum, identifying the specific contribution of a single neutron star merger or a rare type of supernova from billions of years ago. We stand on the precipice of discovering a true population 3 star, of directly observing the formation of planets in galaxies far different from our own, and of mapping the dark matter distribution of our galaxy with unprecedented clarity using stellar streams as our guide. The cosmic archive is vast, and we have only just begun to learn how to read its first few pages. So the next time you find yourself under a clear, dark sky, I invite you to take a moment. Don't just see the stars as anonymous points of light. See them for what they truly are, billions of historians, each holding a unique fragment of the greatest story ever told. See the brilliant blue young stars, scribes recording the recent history of the spiral arms. See the faint red dwarfs, ancient archivists preserving tales from the galaxy's wild youth. And see our own sun, a middle-aged scholar holding a detailed record of the local galactic neighborhood. It is all there, a glittering library of light waiting for anyone curious enough to learn its language. This journey of discovery belongs to all of us. Let me know in the comments which stellar memory fascinated you the most, and be sure to subscribe so you don't miss our next voyage into the depths